We're live. We're live.
All right, everyone. This is another Wolfram Institute live science stream. Today we have a unique format for you all. As you can see, we have more attendees than we usually do. So today we're going to host our first fellow research review session. So for those of you who have been following our streams, as you know, on each particular live science stream, we usually discuss, some particular topic, issue, problem that's at the forefront of the research that each individual fellow is doing. And we don't take that much time to synthesize, to assemble, to consolidate the work that our fellows have done. And so we like to set aside some time every few weeks or so for the fellows to present the work that they've done so far, or at least the work that they're comfortable sharing at the moment, and to get feedback from others in our greater orbit, including Stephen himself, but also some of our other research affiliates. So what we're going to do is we're going to give each fellow the opportunity to deliver a presentation. I imagine it'll be somewhat of a dynamic presentation with interjections and questions, and it's probably not just going to be like a monologue. I'll introduce and try and motivate and contextualize each of the presentations, and then we'll have some discussion. Even if there are kind of different interjections, we'll have some kind of discussion at the end where people can ask greater questions, and we can discuss the kind of the next steps for these individual projects. So our fellows are Nick, Carlos, and Łukasz. I'm going to introduce them one by one, and then we'll begin. So let's begin with Nick. So Nick is one of our physics fellows. Nick, I would say, has a rather demanding challenge to confront, and I think so far he's done actually a pretty good job. So Nick is doing research on our physics project. Now, let me say a few things about some of the goals of the physics project, because the physics project has been under development for 2 years, and it will, likely remain a work in progress for some time. And so, the personnel will change.
I would guess.
Well, yes, but the initial work should not take centuries, right? So, I mean, with time, yes, there will be maybe different schools of thought, there'll be different individuals, tools will change, but there has to be some core underlying set of objectives that should remain constant if it's going to constitute some research program in a proper sense. So what are we trying to do? Well, we're trying to develop fundamental theory of physics that is constructivist, discrete, emergent, structuralist, background independent, and observer dependent. This is my kind of philosophical, concise description of what we're trying to do. And one of the key aspects of that is the constructivism. So especially when you have a constructivist theory of physics, and even things like particles need to themselves be built from some sort of underlying computational constructor, it's a highly cumulative endeavor. You have to really make sure that your fundamental building blocks are correct. And in our case, the fundamental building blocks are the most kind of elementary ontologies that you can think of. So even things like mass, energy, velocity, they need to be constructed in the right way. And not only do they need to be constructed in the right way, but because this is also an observer-dependent theory, anything that we ourselves as humans regard as being physical has to be both constructed in the model, but then also has to be extracted by observers that are endogenous to that model. And so what Nick and I have been doing is we've been revisiting the kind of inventory that was given in the 2020 book, outlining possible kind of speculative interpretations of different physical quantities and revisiting them. And so Nick has been developing a kind of observer theoretical framework for extracting values such as mass, energy, and velocity. And well, I shouldn't say more than that because I think that he can basically present it himself. So without further ado, Nick, please take it away and tell us what you've been doing.
Okay, let me share this. Okay, so this is like the only slide that I have that have text in it almost. The only thing that already you have to read here is that this mandate by James that he already just spelled out to you, and that we put a big emphasis on observer-dependent theory that we're trying to build here. So that's the only setup for this kind of work. And when you ask this question, what kind of theory, observer theory would look like, you start to look for some research. And the first research I encountered in this work on basically the observer-centric foundation by Kevin Knut and his approach to special relativity and how you can describe the quantities from purely observer theoretic perspective and some events and their projections. And because we already have events in our framework, the Wolfram physics projects, though they arrive from the algorithmic set theory, where our algorithms are Wolfram models and other kinds of computational models, this observer theory can begin with just arbitrary causal sets. This is one sprinkled here, and the observer is basically any chain or time-like curve for this causal graph. And similarly, when you have some branchial overlapping events or like any ambiguity in your computational model, your observer can branch, and now it's not longer a single chain, but like multiple chains. So this is kind of objects are representative of observers. So next,
just so everyone feels comfortable interjecting, maybe I'll make the first interjection. So basically, that first observer chain is essentially kind of a discretized version of a world line. Now, in the example on the bottom, it's really no longer a world line. It's actually it's more complicated. But you can think of it that way if you have experience studying special and general relativity.
The thing at the bottom is a causal graph, but for whatever reason, you have branching time-like curves on the causal graph, right?
Yeah, it's a multi-way causal graph now, constructed computationally. This is like a pure causal graph, which is single way, which was in this case was sprinkled into the actual underlying spacetime.
Right.
Here's
So
multi-way causal
in
graph.
the ordinary causal graph, an observer, your minimal model of an observer is a single time-like curve. In a multi-way causal graph, your minimal model of an observer is a branching time-like curve.
Yeah, it's an elementary observer. If you have it computational, you can think of it as tracking a single atom of space or EM for your causal graph. And when you have a single way, your tracking only will produce a single chain. When you track it through the multi-way causal graph, it produces multiple chains.
Yep.
All right. Okay, next. So next, this is what kind of projections you can do on this. So the task here is to actually quantify somehow all the events in your causal graph from the observer perspective. So you pick a chain, and now you can talk about how other events relate to this chain. And you can do it in multiple ways. If you have a single chain, you can basically project forward and backwards on this chain in the future and the past and see for the intersection, the most closest intersection with that chain, right? That will basically tell you two numbers, the proper times along this chain. And with these two numbers, you can infer
Hold on.
one plus
one. For every event off the chain, you generate its light cone, and you look at the first intersection of that light cone with the actual time-like curve that corresponds to the observer. Is that correct?
Yes, exactly. Yeah.
Okay.
So only here you can only show, you can't quantify every event. You can only quantify when there is an intersection with that chain, with both in the past and in the future of that observer. So not all events will be quantified with a single chain.
But hold on. So a given event might have a direct path to an event on this time-like curve, but most of the time it won't. Most of the time it has its own light-like curve that is the edge of its light cone, and that light-like curve intersects this time-like curve. Is that correct?
I'm not sure what's the difference. You just when you make a vertex out component or a light cone into the future, you find the intersection, and what is the smallest event in that chain that is intersecting your cone that you just projected. That would be your projection. And you can do it both into the future and into your past for every single event. And when there's both those projections present, you can quantify it and embed it into 1+1 dimensional space-time.
Yes.
So this is the embedding that it shows an embedding using a single chain. And you can do a similar thing, but using two chains. But now you only require a forward projection or even a backward projection.
Okay, what are the connections that are showing here? So an event off
causal edges.
Okay, but so I see. So for every event here, you are including those causal edges, which are the minimal set that get you to the time-like curve corresponding to the observer. Is that right?
Well, yeah, you can think of it. We just find the projections, all the events that we can quantify, and just take a subgraph from the original graph.
Yes. But wait a minute. But any event that is in the past light cone or the future light cone of any thing on the time light curve is included here. Is that correct?
Yeah, because if it's going to be included, even not on the chain and not the event that we are quantifying, it's also going to be quantified, and it's also going to be in the same set, right?
Right. But by quantified, you mean you count the number of causal edges from some point on the.
Well, you're not counting the actual path from the event to the chain. You just you find the event which is the projection, and you know the proper time because you can think of the actual chain as a clock. So
Yes.
or any foliation slice that you can use, and those numbers are quantifying those events in the past and in the future. So these two ticks of a clock allow you to embed it into 1+1 dimension.
Okay. What's the picture below?
You do it the same thing, but for two chains now, and you only do the forward projections. Like every event here, you project it forward on both of those chains, and you have two proper times now that relate to two chains independently, and you do the exactly same embedding procedure. And now somewhat you can think of it like they now embed in between of those chains, and also in 1+1 space-time. And similarly, you can do the backwards one, but I'm not showing it here because it's not very physically how we think about this kind of measurements of events we're doing. All right, let's jump next. All right, so this is the transformation thing, which a lot of intuition came from Kaufman's work actually on his special relativity derivation from a bunch of iterant algebras and so on. So here you have, again, as in the previous slide, two pairs of chains, two observers that we can quantify all the events around it. Right here, the like red pair and blue pair is all independent observer pairs that we quantify events with. Right? If we pick two arbitrary events and a vector and any vector between those events, the transformation between these vectors would be like some combination of scaling and the booster notation or whatever. What you usually think of when you talk about Lorentz transformation, usual special relativity. Here you require also for each vector in this embedded space-time, you have two parameters, scale, and the most natural one is this K factor, which is related to Doppler shift. You don't have to think about it too much. Basically, you need two parameters in order to make a transformation from one observer coordinatization to another one. For every vector you pick, your vector may be like not representative of any particular causal edge. It can even be like backward directed. It's just like any vector in your space-time.
Wait a minute.
So if you wanted to execute, say, an overall boost between two pairs of observer chains, you effectively have to compute that one vector at a time because everything is discretized and you don't get the normal properties that you would normally expect.
For nice coordinatized inertial observers, your parameters of scale with K factor would be the same along the whole chain. But when you have like general, very rigid chains like that, you have to do it independently for every vector here.
Right. So I mean, but basically what you're trying to do is you've got these two time-like curves, and you've got each time-like curve has.
Well, you have four actually, right?
Yeah, four time-like curves.
You have two pairs.
Paired. Yeah. Because like in the previous slide, we used pairs in order to quantify events. So we quantify with this scheme with two pairs.
So in other words, you're kind of giving an XY coordinate, but you've got two clocks, one on each thing, and you're like a little GPS system in 1+1 dimensions. You're quantifying position by knowing the time stamps at which light pulses reach you on each of those time-like curves. Is that correct?
Yeah, it's correct. You basically only can do 1 + 1 because you only can say which time it is and how far your radial distance is from this event.
Yeah, right.
So you only compute
1 +
radial
1
distance and time. Yes.
With
And how we can escape this 1 + 1 dimensional space-time is the whole deal. It's like there are many directions we can take from there.
Right. I'm not worried about the 1 + 1 dimensions. I'm sure you can do, just like, I mean, it's an interesting question. How many, basically in a world where we have an unknown number of dimensions, you can have the 3 GPS curves, so to speak, 3 GPS clocks, and you'll get some distance. And if it's a 3.7 dimensional space or something, you won't be able to get full,
Yeah, that's like the obvious extension to this idea. Just if you want more dimensions, just add more observers, more observer pairs, and do the same coordinatization procedure. Then you kind of somehow combine them. And what is the minimum dimension is it required? How the minimal number of pairs of observers is required is your dimensional spacetime.
Yeah, right. To get yes. I mean, there's some discussion actually in the physics book about this way of thinking about orthogonalization of directions in order to resolve positions in arbitrary d-dimensional space. But okay, this is cool. All right, so I'm still not quite understanding. I mean, you're describing here, presumably, if your original causal graph had some very simple form, maybe a grid graph, maybe something like that, these transformations from one world line to another would be very straightforward. And is there a case where you can get sort of simple mathematics that describes, like, say, Lorentz transformations in that situation?
Oh yeah, for example, the Knut papers on how he's doing this, he's not doing it on very rigid causal graphs like that. He always assumes nice inertial observers, and derives all of the causal, all the special relativity transformations.
All right, keep going.
And even on the grid graph, your observer chains in general can be very rigid. You don't have to pick along the grid. You can pick like all kind of moving chains there.
Anyway. So that's one of the challenges, is that I think Nick has been able to rely on some precedents in the scholarship. They basically pick the low-hanging fruit, and this case is much more challenging. Yeah. All right.
So now there's also a way to do some dynamics with these kind of ideas. If you pick any observer, now you can think of it as a particle, and then sample a bunch of chains around it, which you can think of other observers, and do this particular projections of any event on this particle chain on all other observers, and just compute what kind of, instead of computing intervals like before and embedding them into 1 + 1 dimensional spacetime, you now compute a rate of influence, like how many projections this particle have on each of the observer. Right. So this is now you compute not the interval but the frequency, so the conjugate pair to spacetime coordinates. Right. Now you compute two rates. Similarly, you compute 2 rates forward and backwards in time, and now you have 2 numbers. From those you can compute energy and momentum, and your usual special relativity equation can relate those. And now you can, because you're sampling a bunch of chains, you can plot a histogram out of those and just see how this particular particle, what kind of spread of energy and momentum it has, depending on which observer.
So you're saying, I mean, if you take the limit on a flat space-time of that particle, do those things become Gaussians that become sharper and sharper?
Well, presumably, yeah.
What's that?
Presumably, yes. Yeah.
It'd be nice to see that. I mean, so in other words, what you're basically saying, let me try to understand what you're doing here. So this is a classical, there's no multi-wayness to this whole thing. This is simply asking, based on these probes, okay, you're assuming, okay, so in the case of the localization by GPS or whatever, at every point on the world line, you're trying to make a localization. And since the world line is moving, you don't expect the localization to be the same at from every one of those probings. But in this case, you're making an assumption that along the world line, the energy and momentum and so on is constant. And then that means that by these different probings of the world line, you're getting, you're getting different estimates of that. And you're here showing a plot of all those estimates of what you think should be the same energy momentum. Is that correct?
Well, for special relativity case, energy and momentum depends on your frame of reference. Here, you also, if you pick any vector along your particle curve, right? And if you project it on different observers, along the whole chain of observer, right? You can compute how many intersections on any observer this particular vector have, right? And this would quantify the frequency of influence of this particular particle on that observer. And you can compute this rate for any observer, both into the future and to the past. And this kind of scheme will allow you compute energy and momentum.
Maybe you should
very similarly.
Go ahead.
Yeah, that's it. Yeah, there's nothing else to say here. This is also it also Knut's idea to do how to do it. So it's not original in any case, but applying it on the causal graph.
Okay, see the concept that the energy density on the causal graph is that energy density is proportional to the number of causal edges that go through a space-like surface. You have a more microscopic version of that here, because you're not talking about a whole space-like surface. You're talking about something which is related to a single world line. Is that correct?
Yeah. And I guess if you do it for every possible world line and average it out, that would say something about the whole causal graph.
And the energy density everywhere.
Yeah.
But what you're saying, what you want to get here is a way of estimating the energy associated with that individual world line that you're interpreting as a minimal model of a particle. Is that right?
Right. Right.
It's not self-evident that a single world line can support a particle.
No,
these are not actually particles. There's no way, because these are just events. No, nor are they observers. That's also kind of a misnomer in the special relativity literature. These things cannot perform observations, and they also don't have the requisite properties to really be particles. But with coarse graining, once we actually do have models of particles, you could take that model, which will be more elaborate, and coarse grain it so that it looks like this, and then you could do the same thing for particles and measure the velocity, etc.
Dynamics of the causal graph are, which we don't know. But I agree, this is a good minimal model. Let's see, Nick has more.
No, causal set theory knows about how to do dynamics for causal sets. You just in bulk count the number of events and all kind of size of chains, and that's how you define action, and you can do dynamics. But it's not very constructive, so and we don't want to go into that direction.
We have a more useful way of doing that, but it's okay. You should keep going.
All right. So this is another intuition of how we can escape this one-dimensional space-time. There's a notion of 2D orders, which is a special case of a partial order that can be nicely embedded in 2 dimensions already, right? In order to construct it, you start with a total order, and then you can sort all of your events with that total order. If you want 3-dimensional order, you start with 2 total orders, because 1 is arbitrary, and you can embed those events into 3-dimensional space. There's no nice procedure to determine whether your given arbitrary causal graph is 2-dimensional, 3-dimensional, how many total orders is required in order to define it. But you can at least sample those kind of causal graphs. And that's how causal set theory is doing it in some cases in order to study dynamics.
What you're saying is, you define a total order, you have 2 different total orders, and each total order is like a coordinate labeling for one particular coordinate. The total order,
time and space,
a single coordinate sequentially.
Yeah. So here is
just as your world line is defining a total order among the events that are in that world line.
Right. Yeah. So, one chain is one-dimensional,
right,
and it's just a single total order. If you want to embed it in two-dimensional, you just require second one, and now you can do n factorial of those, and you can like come up with some brute force way of enumerating this. And that's what I did. This is like very hard problem actually, enumerating all the posets. This is like this is the number of all deposits with a given number of events, right? This is I did this same kind of thing, but the special 2D orders, and they start to differ at the event of when you have at least 6 events, and just to see what kind of causal graphs says that are different and can be embedded in 2 dimensions. Is these 3 causal graphs, the difference between these guys, right? And the idea here, nice idea would be here to extend this to the 4-dimensional case and find the minimal case when 4-dimensional orders are different from the arbitrary poset, and find those as some kind of invariant that you search for in arbitrary causal graphs in order to define some kind of particles. Because as soon as you have some causal order that's clearly locally not embeddable in 4 dimensions, that should be necessarily some indication of a field present. So that's the idea of a field, quantum fields, or whatever matter.
What's the 4-dimension thing got to do with anything?
Well, because if you're given a causal graph and you know that you can't embed it in the 4-dimensional one, right? You require some additional term to your Lagrangian or whatever you want, formalism you want to define it, in order to define this particular piece locally.
I think you're taking
the dynamics of it
way too seriously. I mean, I think that it's a deeply static formalism.
Well, it's deeply static, but as soon as you like constructively take any computational model that produces a causal graph, which locally has this piece that clearly not embeddable in 4-dimensional with 4 total orders, right? This clearly is not going to be limit to any Minkowskian spacetime.
It's the wrong thing to look for at this stage. I mean, there's
Why?
What's that?
Why?
Because there's going to be nothing special about 3 and 4 dimensions. It's just not. It's not. I mean, that's one of the learnings from what we've done so far. Is it'd be lovely to derive the 3. I don't think this is the way you're going to get there.
Well, I think the 4-dimensional kind of special. I think there's because there are some natural ways to find additional 2 degrees of freedom for arbitrary causal graphs, which is kind of.
I don't believe
which kind of outline some of these ideas in this last slide. So we're kind of finishing up. So
wait, what did you say, Stephen? What were you mumbling? You don't believe it?
I don't believe it. I don't believe it. I don't think that. I think it's a mistake. I think it's an engineering solution. It's the same mistake people have made for decades, trying to engineer discrete physics and so on. It's just a mistake.
Well, that's kind of less engineering in some respects, because when you have just arbitrary undefined space, which is your hypergraph or whatever, which is evolving, have arbitrary fractional dimension is kind of more engineering that just take an arbitrary order of events and try to find some relations that can describe these 2 additional degrees of freedom. I think it's more, for me, it seems more natural.
Look, I think that to make an observer capable of observing 3 + 1 dimensional space seems reasonable. And to see what happens with that observer, just like you make an observer capable of observing 1 + 1 dimensional space and see what kind of a thing that observer observes. And, perhaps what you find is that there's something special about observers who are 3 + 1 dimensional observers rather than observers who are looking for 1 + 1 dimensional space. But I think, one of the things you do seem to be doing here is, by virtue of thinking about observers as, I mean, I don't completely understand this, but by the time you're making observers by counting time-like curves, you are going to wind up having integer dimensional, you're going to wind up having something special about integer dimensions. If your model of observers involves 1, 2, 3, 4 type time-like curves, you will discover that there's something special about integer dimensions. Whether that's
No,
correct.
it is special.
What's that?
No, that's it. I think it's special. It's just any, but I'm not saying that fluctuations from integer dimensions are not possible. It's like I described this with 2D orders here. You can have an integer dimension that can be nicely embedded and think of as a space-time, but you have like some fluctuations that describe matter.
Yeah, but zooming out a little bit, okay? One of the things that you are implicitly assuming, which is not obviously stupid, is that, you know, observers are integer dimensional kinds of things. By virtue of the fact that instead of, you could imagine, you know, you are having an observer who is made up of a, you know, 1, 2, 3, 4, 5 time-like curves. And you're using those as your kind of fiducial things that are what the observer uses to measure what's going on in the world. And I think that's not unreasonable, perfectly reasonable place to start. I think, yeah, I mean, that the thing you're highlighting of spatially and branchially extended observers, that's obviously more complicated because, you know, by the time you're just dealing with single threads, you know, yeah, I mean, that seems like a much more complicated story.
Well, yeah, it is. Yeah.
But Stephen, I still don't quite grasp what your critique is besides general expression of suspicion.
I just think, look, I think the methodological approach of asking the question, if you make a minimal model of an observer and or a particle that is a single world line, single causal edge, single time-like sequence of causal edges, that's a perfectly reasonable thing to study, okay? And I think that, you know, extending that to bundles of causal edges, again, seems like a perfectly reasonable thing to study. It's going to get much more complicated when you have bundles of causal edges, because you have to define, just like, you know, just like in the case of curvature in space-time, you're going to end up with these things which are essentially, you know, as that bundle moves, that bundle will deform according to the effective curvature of the space-time that it's in. And that's going to get kind of complicated to model, I think. But I don't have any objection to any of that. I think the mistake, in my opinion, is I would not jump. I would just analyze that and try and see what you can figure out from that. I would not jump to interpretations in terms of traditional physics until you've gotten further in analyzing what's going on. I mean, you can use those as you know, if you choose to use those for intuitional support, fine, but I wouldn't jump to those interpretations before you, I mean, you know, the first step, it seems to me, is we've got a causal graph that presumably is generated from some underlying dynamics. You've then got a time-like edge, or two time-like edges. I like your idea of projecting onto the, in other words, what does the world look like to these two minimal observers? It's kind of what you're saying. And I think you need kind of a diagram, which is, I think, what you were doing, but I didn't quite get that diagram. I mean, it's a you know, how do you plot out what the world looks like? I mean, like for example, we are used to making simultaneous maps. We're used to making maps of the world in which we show all of space at a fixed moment in time, in some sense. You know, when we make a picture, you know, okay, it gets a little bit non-trivial. Make a picture of the solar system, okay? Solar system has non-trivial, you know, this is an issue for version 13.2. You know, we have the ability to make a picture of the solar system. And the question is, at what moment is this picture made? It depends on, you know, it depends on the reference frame, depends on foliations and things, because the actual configuration. So my question to you is, in that setup, if you were making, you know, what you've got is a different, from a two world line view of the universe. It's a little different than the single space-like hypersurface view of the world, right? Can you compare those?
Yeah. Yeah. Well, even in the real world, it's not immediately obvious that we live in like four-dimensional space from the perspective of a single particle that just merges some signal coming to it. How can it tell whether it's right? So this is a model of an elementary observer, like this kind of particles that have no notion of direction and just measure some incoming informational signals. And that's the worldview.
I'm suggesting, intuitionally, it will be useful, just like we imagine things like Penrose diagrams for conformal sort of representations of things and so on. I'm just curious, in our usual experience, we make space-like surfaces and we draw, topography on space-like surfaces. We draw geography on space-like surfaces. My question here is, it's like, if you're a fish or an insect or something and you're viewing the world, and let's say you're an insect with multiple little, eye homatidia type things, and you're using those to view the world, you will construct some impression of the world. So similarly here, your two-world line, observer family will construct some view of the world. And I'm just suggesting it will be interesting to see what is that view of the world? I mean, you're showing a picture.
Oh yes, that's the objective of observer theory overall. These are pathetically, these are minuscule observers. These are just individual particles, which unless we're panpsychists or whatever, we don't believe that they're actually performing observation. Real observer theory has to actually take into account the computational faculties of the observer itself, and we're not even close to that yet.
Complicated thing where you've got whole bundles of causal edges and you've got all kinds of fast and slow dynamics and all kinds of things like this.
Well, but you also have to account for why it is that this particular bundle is also capable of performing, computations in its own right, which is another very complicated aspect to this.
Yeah, but so okay, what's the roadmap here? I mean, I think the roadmap. Go ahead. Yeah.
I don't think we have. Well, in addition to this, I'm not sure what. More, like what exactly would you be describing? And more, we should focus on more how actually observer computing things, right?
Yeah.
And how this boundedness of an observer. So it's related. The plan here can be to actually take some computational model like Wolfram model and see what kind of inferences can observer have, like this chains, elementary observer chain can have on a.
It will be good to start off, it seems to me, giving, as clearly as possible with the formalism that you have, how does special relativity work, for example? Exactly how do you construct boosts? How do you construct, what happens? How do you make, you say you pick a time-like curve for an observer. Okay, you're going to pick two different time-like curves. Those are effectively two observers in different states of motion. How do you, it will be really good to see explicitly how those two different observers in different states of motion, how they see, standard Lorentz transformations.
Well, that's what we showed here, right? This is like how one observer sees it, and this how another observer sees it. And
I guess I'm asking for a little bit more detail here. I'm asking to actually derive, Lorentz transformations, which shouldn't be
well, it is derived here. I'm using the actual transformation. It's not just some visualization trick. I'm using an actual transform with these two values. Instead of a velocity, what you have in an actual special relativity case, you have a velocity of observer, and now you can do a boost, right? And here you have, instead of velocity, the more natural way is to use a Doppler shift, this K ratio. And because you don't have very nice inertial coordinatized observers, you also have to introduce some scaling. So you have two factors, two parameters in order to transform arbitrary vectors.
This is a fine picture, but what I was asking about here is a very step-by-step way in which you can see that, what falls out of this. You can see the Koch, Cinch, matrix and all those kinds of things that you can really see explicitly from something which starts off as just a pure sort of causal graph, for example, generated from hypergraph rewriting or whatever else, that you can actually see that you get, and under what circumstances you get Lorentz transformations.
Well, you can have it as soon as you have any order. Well, that's the point of this, of all the papers from Knut and Kaufman. As soon as you have order and some kind of repeated pattern, you can derive all the special relativity quantities. Okay, you can derive hyperbolic numbers, and they'll naturally produce all the Lorentz transformations.
Then let's see it explicitly, step by step, very carefully, in my opinion. I think that'll be very useful.
Well, I'm not sure what explicitly going to mean here.
Well, I mean, you should be able to explain this, okay, to, high school level, whatever. You should be able to say, here's a picture, here's a set of things, here's a set of curves. You can see a limit that's, because this is still, these curves are very wiggly here. I'm not seeing a cinch function coming out of this.
Well, then I don't see how causal graphs and discrete algorithmic sets can help with this. You just go to the paper when they already have this nice lines of observers that don't even discrete in general, and they derive all the cinching cosh functions there.
Okay, but we should be able to see that as a limit of these discrete things.
Well, it's not even a limit. It's just a property of a hyperbolic number which can have integers.
Then I don't believe it. I don't think that's right. I think that if that's what they're doing, then they're doing something kind of trivial. I don't think it's a trivial thing that just comes out from the structure of the model. I think you have to do more work to get to it. And I think that you should see it as a limit. It should not be the case. I mean, like for example, if you have, I think one of the goals here, you're trying to construct a coordinate system derived from a bunch of clocks that live on different world lines. That's a very sensible thing to do, but it just needs to be, look, it should be the case that given a causal graph, given a world line, a set of world lines, it's like, and maybe you already have this, it's like construct the effective structure seen by those clocks in whatever projection it is, which isn't the usual thing we're used to, which is pure space-like slices. It's some other way of viewing the world that we're not particularly used to.
Well, as soon as you embed these events, even you started with a nice integer projections, and as soon as you embed it, you can clearly define angles between those vectors. And as soon as you have angles,
so the embedding is intrinsic, based on this timing data. Or
yeah, just take two time indicators that you measured, proper time along the chain. These two numbers you take, it's their sum and their difference, and you get time and space dimensions.
Yep.
Right.
Okay.
So then as soon as you derive this embedding, which lives in the integer grid, but you can define angles, and you can talk about immediately about not just velocity, but those.
But if
rapidity.
you change the world lines that you're using to define these things, you're going to change that representation, right?
Yeah.
There should be some stability, under changes of the observer world lines. And that will be a limiting property. It won't be a property that's true of individual world lines.
Yeah, so as soon as you have very dense causal graph, you will be able to find nice inertial observers there.
Right, but I think it will be good to see that. It will be good to see that. It will be good to see how we get a large causal graph generated algorithmically, because I don't think it's going to work for an arbitrary causal graph, that you can then observe that, yes, you get these inertial observers, and you can see that limit actually works.
Okay, so your suggestion basically to look for inertial observers in algorithmic causal sets or causal graphs.
Yes.
That's what
something where you can take a limit where you can actually take a limit and where you're not just putting down random points. I mean, it might, you could also look if you want in one of these random point type things, but I think it's going to be less. Those random point things are going to have a hard time knowing, how they should have points sprinkled. But then what we want to see is that, what are the assumptions that are needed in order to get special relativity? Which I think we partly know. I think we kind of know that, but it would be nice to see at this level of explicitness. And then how do you get, because in general, you wouldn't expect to see special relativity everywhere. You'll expect to see general relativity, or something more general than that.
Well, that's why we don't have inertial observers in general here. That's why it's more general than special.
No, I understand that. But so then you should be able to see, look, there's got to be consistency between observers, for example. These two different choices of observers better perceive the same gravitational field, for example.
Well, that when we want to talk about gravity, that's going to be more complicated.
But if you don't have an inertial observer, you've got a gravitational field, effectively.
Yeah.
So
we can measure acceleration.
Sure.
Some kind of.
That's what I would do. I mean, I think that. Let me see. I mean, the main thing you're doing here, as I understand it, is given a causal graph, you are. And picking a time-like curve in the causal graph, or a few time-like curves in the causal graph, you are then working out something which I don't think we've really done before. We've looked at causal graphs and things like causal cones in the causal graphs, but I don't think we've really looked carefully at this idea of world lines in the causal graph. What can you conclude from world lines? I like your idea of the effective projected coordinate system for an observer on this world line, or an observer with access to the clock data from two different world lines.
Yeah. You can think of them as soon as observers meet at some point, they just compare notes of what kind of measurements they did of all the events and their clock measurements, and and come up with this nice common observer, common embedding.
Right. So that's the single way case. And then you've got the multi-way case of this.
Yeah.
Which we've barely probed so far.
Right. But I think there's more to do even in the single way case. I just think, I think this is, there's more step by step here. We should probably move on because we're really getting behind time here.
Yes. I suspected that the initial discussion would basically last an hour. We still have two presentations. So let's move on to Wukash. Okay, Wukash is going to discuss something that's just completely different from world lines. So Wukash has been working on computational Langlands. I should give a bit of an introduction to the computational Langlands program. So we had worked in the past on taking entries from formalized math libraries and studying their relations via computational means. Stephen originally called this empirical metamathematics. And in empirical metamathematics, one can gain this kind of aerial bird's eye view perspective of the general mathematical landscape and the dependencies, the correspondences that constitute it. And so I began to develop an interest in applying some of these techniques to the study of some sort of research topic in mathematics that is well known to span, straddle, and pervade across multiple different areas of mathematics. And of course, Langlands stood out as a natural case study. So we thought, okay, maybe we could apply this to the Langlands program. However, there was a significant obstacle, which was wishful thinking on my part, which is I thought, okay, well, we'll take all of these theorems that are residing in these formalized math libraries on the Langlands program, and then we'll study them via computational means. Well, they're not there. I've spoken with Kevin Buzzard and others about this. Apparently it's quite difficult, and they're struggling considerably to actually even verify and basically instruct computers to understand these various conjectures, theorems, and proofs about Langlands. But that actually motivates an important theme that I'd like to underscore here, which is the role that computation will play in the future of mathematics. There's a certain camp that's quite bullish on math formalization, on proof assistance, and on verification by computational means. But, and Richard Borchard's actually made a nice kind of statement about this when he was speaking about computers and their role in proof theory. In order to be able to properly convey to a computer some particular theorem, some particular proof, we have to understand it quite well. And there are many aspects of topics at the avant-garde of mathematics that we really do not properly understand. And computation can also be useful for understanding these areas of mathematics, especially when culturally they become somewhat occluded, or even because they're vast and they have so many dependencies that even individual specialists are not familiar with the entirety of its scope. And so what we decided to do is, instead of just importing with convenience these different theorems from these math libraries, we would make Langlands itself computational. We would dive in, we would understand the concepts, the theorems, the history involved, and step by step, we would make these things computational, and then we would explore the dependencies of basically our own homebrewed version of Langlands. And in doing so, be able to provide an overall kind of cartography of what this program is really about, coupled with the understanding that we'll have garnered after having, step by step gone through the painful process of actually understanding not only what the mathematics is, but often what the mathematicians are struggling to say or saying in a somewhat indirect or unhelpful way. So Łukasz has been, and I think Łukasz has done a very good job, because he came into this without experience in Langlands, and Łukasz himself will explain what Langlands functoriality is, but I'll just say something briefly about it so that you understand the scope of his presentation. Langlands functoriality concerns the equivalence between two different types of L functions, which are two different types of Dirichlet series that you consider in analytic number theory. One of them is basically on the arithmetic or number theoretic side, and these are Art and L functions that were originally used within the context of class field theory. And another are these automorphic L functions, which, supposedly putatively reside in a completely different area of mathematics, and there's a correspondence between them. So we obviously had to begin on the arithmetic side, and I would say that on a conceptual level, we can explain class field theory, we can explain these Art and L functions, and Łukasz has been able to actually do computations with these L functions. So the roadmap here is, now we have this for class field theory, Łukasz is going to kind of explain it to you guys, and then we're going to do the same thing on the automorphic side. And then there's this kind of group theoretic treatment of these functorial relationships, and we can actually start to make these things computational, and we can actually start to assemble everything that we've learned about Langlands and throw it together. Right now, it's mostly been a theoretical romp, which has been actually quite fun. So Łukasz, why don't you go ahead and explain in a gentle and introductory way to people, many of whom might be interested in Langlands but have never actually had the courage to look at it. Explain what it is, and then let's look at some examples of some Art and L functions.
Okay, so I expect everyone. Can you hear me?
Yes.
Yep.
Yeah. Okay.
I can see you, but not your screen.
Sure.
Are you trying to share, Łukasz?
Yes. I'm sure.
Okay. Should I filibuster?
I think I got it. No, okay.
We still don't see anything. Okay.
No.
Started. Nothing yet.
Okay.
Okay. So I just want everyone who doesn't understand something to interrupt me and make this presentation more conversational, and we can decide how deep we want to dive.
So the definition of an L function is that you
Well, Lukash, let's let him think. Lukash is a careful speaker, so you can interject, but you got to let him say the first word. Oh my God!
Like, L functions actually doesn't matter that much in this setting. Like, they're just sort of analytic tools to extract properties of the arithmetic sequences. You can basically prove a sequence by generating a function from it and proving some analytic properties of this function.
But Lukash, you're jumping ahead. There's some nice progression here that begins with class field theory, algebraic number theory. We've discussed it many times. Just walk everyone step by step through what abelian class field theory is, please.
I mean, as I understand it, we've got these characters, we've got a list of characters which are, and we're going to make something like a zeta function, except that it's not.
Yes, yes. But
go ahead.
Okay, we have field extensions, and we basically want to study field extension and how different prime splits when you extend your field. So, for example, in Gaussian integers, 5 is no longer a prime, because you can express this as the product of 2 plus I times 2 minus I.
Mm-hmm.
And basically, class field theory studies these things like in a general setting, in arbitrary number field extensions, and studies which prime will split and which will not.
Class field theory is just
over this.
Yes. Class field theory is essentially the study of factorization and the extent to which it can be unique and the extent to which it fails to be unique. And I mean, Lukasz, you're going to explain ideal class groups, class fields, and why this thing is called class field. You're going to explain all this, yeah?
Yep.
Okay.
I actually have my text here, so you don't need to read this. I just have it for me. Okay, so you basically have this huge theorem that states that you can represent the Galois group of your field extension with something called Hecke characters.
I want to just say, hold on, Lukasz. I mean, maybe you're a little nervous. I just want to maybe I'll set the stage just slightly so that Lukasz can then intervene. Okay, look. So, what is this whole Langlands business? Langlands basically generalized this term known as Artin reciprocity. Artin himself was interested in class field theory. He was interested in particular in the non-abelian case of class field theory. So what is class field theory? So as I said before, class field theory is the study of unique factorization and the extent to which it fails. So in this case, we're studying not just primes, we're actually just studying ideals, prime ideals, principal ideals, non-principal ideals. There's this thing in class field theory called the generalized ideal class group. The generalized ideal class group basically tells you how far off you are from unique factorization into principal ideals. And there's a thing called a class number, which you probably know, Stephen, because it's a function in Wolfram language from 2007. And it basically tells you how messed up this particular case is when you're trying to factor uniquely. Okay, so this thing is called the class number. Okay, so what happened was, as people were beginning to develop class field theory, it seems as though they wanted to ensure that they had new constructions such as these groups and these fields, and that they could study them with generality. So what they did was Dirichlet, and I mean all L functions are Dirichlet series, so Dirichlet is like an original figure in this field. Dirichlet himself had a theorem when he was studying the arithmetic progression of primes that Z mod mz ed star contains an infinite number of primes. And what Weber and Takagi and these other people in class field theory wanted to do was just show that when they were developing these new objects, they could still study them generally. And that's basically what Langlands is also trying to do. Okay, so I'm not sure how much detail I should give, but one important thing that happened, a couple of important things that happened. One is people began to develop these class groups, and then subsequently these things called class fields. So you have some ideal class group. It's a quotient group of basically your ideals. They're called fractional ideals, but it doesn't matter. It's a quotient group of your ideals and your actual prime ideals. And so what was discovered is that you could take these things called class fields, which are a different object, but the Galois group of these fields and these original groups were actually isomorphic to each other. So all Artin did was develop a new kind of L function that reduced this whole question of class field theory down to the study of the Galois group of various field extensions, which I suppose is more general and as we'll see, perhaps Łukasz will describe this as more convenient. So this is really what Langland's program is all about. It's just about basically extending Dirichlet and Dirichlet's study of L functions, not only to field extensions, but to non-abelian field extensions, so that basically people can rest assured that you can study factorization, the extent to which factorization fails, not just in the group theoretic setting and not just in the field theoretic setting, but in a non-abelian field theoretic setting. Okay, that's basically class field theory. That is what Langland's first sought out to do. Now, this whole thing with automorphic L functions, et cetera, but we don't have to get there. We're just going to start with these Artin L functions, particular L functions set up to study this property. Okay, with that, Łukasz, I've alleviated some of the burden of just motivating what the hell all this stuff is. Now you can provide some more of the detail.
Okay, thank you, James.
Yeah.
So.
Well, no. I'm sorry, I'm still confused about the whole project. Okay, so there's this, there's sort of the view of the Langland's program down in the weeds at the level of Dirichlet L functions. And
it's not really down, but that's not really down in the weeds, right? That itself has tremendous amount of dependency. If you want to look at even Langland's functoriality, it's just the correspondence between these different kinds of L functions.
Okay, all right, fine. Well, that's great.
So those are the trees, I would say, not the weeds, and you can swing from them. That's the whole point of Langland.
Okay. So, but the overall picture here is you want to have a computational representation of what's happening with these L functions and what's happening with these correspondences between different kinds of L functions and so on.
Yes.
Not exactly L functions. Like L functions are a tool which we use to analytically represent some arithmetic properties.
Okay.
So, actually,
I'm going to request some patience in the sense that eventually this is all going to come down to the study of groups. There's a higher and higher version of this that just studies everything in terms of groups and mappings between these different L functions, but we're not there yet, right?
Okay.
What we have today is introduction to the non-abelian class field theory side. Next time, when you see the sequel, Łukasz 2, Back with a Vengeance, it will be the automorphic side of this. And then once we have those two pieces, then in an actual computational, multi-computational, empirical way, we can actually study the relations between them. There's just a serious amount of technical debt.
We
don't know.
Okay.
Just listen to what Łukasz has to say about the first part.
This is being presented in a way that I like seeing math presented, which is just, here's the construction of the thing, as opposed to the axiomatic formulation of math, where you say, here's a theorem, connect these together. I mean, you're giving sort of a constructive way of a constructive computational way of talking about the stuff in the Langland's program. But the thing that I'm a little confused about, I mean, let's just take a really much more trivial example of a duality in mathematics. Let's say between algebra and geometry. Okay. I mean, we have, like in Wolfram language, we have pretty good representations on both sides of that duality of geometrical kinds of objects and algebraic kinds of objects. And I guess I'm curious, because we have all of the machinery built there. I'm curious if there is some functoriality, so to speak, between those things.
That's just a completely different question. Why don't you just listen to what Łukasz has to say about the study that we're actually doing instead of suggesting a different study?
No, I'm just trying to get some understanding of what kind of a thing is going to come out of this. So I mean, this is constructive mathematics, but you're trying to understand a duality in this constructed mathematics. Is that right? Or
Yes.
Yeah.
Yes. Yes, that's correct.
okay. But
And
it's not.
what we
It doesn't look like meta mathematics. It looks like mathematics.
Well,
it is mathematics at this
it
point.
is mathematics. So
We
look,
don't
look.
do this theorem things as James said at the beginning.
There's a bridge between two things in mathematics. In order to show the bridge, we have to understand and be able to compute both sides on either side of the bridge. Each side is terribly complicated. And within 6 weeks, we actually understand the first side of the bridge, which we're explaining, and then we'll show some computational examples.
Go ahead.
That's so look, in terms of the timeline, I would say, Nick's project on observer theory, I'm not sure how long that will take. Carlos's project should probably only take a few more months on sub-axiomatic foundations. This project will take a full year, and the beginning of it is going to be highly theoretical in nature because the lean community, etc., they have not proved this stuff, so we have to compute it ourselves, and we also have to learn about all of it. So unless you don't want to hear a short lecture about what this stuff is,
No, I want to. I want very much.
okay,
I don't understand.
you'll have to
so
follow.
Really
Because you'll have to follow it. As we do this with time.
Okay.
So let's talk about abelian class field theory.
Okay, so maybe to motivate a bit, if you want to see an actual bridge, I think here it is. And this is about as much as you can compress Langland's program.
But Łukasz, no one besides the two of us are going to understand what this is, right?
Show us some explicit examples. You started off with a lovely, explicit Euler phi function generating some nice, Dirichlet character thing, and then, packaging them up into an L function. That seems like a good start to me. Can you go from there? Or go from some other concrete starting point?
I want to motivate my example, what we're actually doing with the Dirichlet character. If someone wants to just print screen this and just keep it on site.
Okay, try.
Okay, maybe I'll move here. Okay. So, what are Dirichlet character? You basically you basically want, for some reason, I may explain later, you basically want to study the representations of your Galois group.
Okay, where did the Galois group come from?
From the field extension that you study.
Okay, all right. So the base thing, we're starting with the field extension.
Wait. Hold on. I said this before. I'll say it again because I said a lot. The whole point is, in class field theory, there are these groups. The order of the group tells you how messed up, how far away you are from unique factorization. Okay, that's the informal description of it. It's a group. Someone established that there's actually an isomorphism between these groups, and Galois groups of these things called class fields, which are related but are different. And this is actually kind of a surprising thing that these two things are related. So what people did was they realized, okay, we don't have to deal with these more complicated group theoretic properties. We can just study class field theory in terms of field extensions in our Galois groups. So you start with a Galois group, and then you take a representation to the complex plane. Łukasz can take it from there. There's 4 characters to come in.
Okay, although what would help me is, for example, in the case of the Gaussian integers,
yes.
There are numbers which are, the numbers which are prime over the integers, not prime over the Gaussian integers. I mean, it's rather straightforward. I've never done this, but I mean, you can obviously take for any given field extension, you just make a list of numbers, and you can say, what characteristics do these numbers have? Which ones are now prime? Which ones aren't prime? You can explicitly see that happen. And that would, for me at least, that would motivate understanding, given the pattern, given I feed in a field extension, then I look at the table, the first 100 numbers, which ones are primes, which ones are not. That would help me to, is that?
The thing is, we are now actually developing all this function because first of all, it took a huge amount of time to get into this thing and understand it. And second, in some very general cases, it is even provably uncomputable. But not for number fields, not for what regular Lagrange is about. I think we can do well with regular Lagrange.
But Stephen's actually making a more modest claim, which is just to motivate this general study of splitting and factorization, just showing some simple examples that someone in high school could understand would be helpful. There could, I mean, look, this Łukasz's notebook can and should, with time, include just a whole suite of kind of educational pedagogical little tools like that.
I mean, so look, if you just say prime Q with Gaussian integers that are true or false, I mean, I can just make a table of if I make a table of prime Q, of n with Gaussian integers that are false, which is the usual case, right? The first 100 numbers, I can say n goes up to 100. With Gaussian integers, I got a bunch of, I got a small number of primes. Okay, so I can say, I'm just going to say position of that, comma, true. And I've got all the usual primes. Now I do the same thing for Gaussian integers that are true, and I am confused because I have fewer primes over the Gaussian integers, right?
Stephen, we don't see your screen, right?
I know you don't, because I wasn't.
Look, guys, wait, let's focus here. Look, here's the task at hand. We only have so much time left for Łukasz's presentation before Carlos takes over. Łukasz has done actually an incredible amount of theoretical work. It's very difficult to unpack. What I had hoped is that we would deliver a relatively simple, cursory, definite description of abelian class field theory and show some computational examples.
Okay.
Now, I think Łukasz is a bit nervous, and I'm not sure the interjections have actually helped him that much. Łukasz, maybe just show an example of an actual Art and L function that you've computed, and we can kind of unpack what's involved in that actual L function, and then we'll probably have to wrap. Not the d ratio L. No, where are the actual Art and L functions that you've computed? You made your own.
Naive, but I mean, if you look at the numbers from 1 to 100, there are 12 numbers that are prime over the integers and are not primes over the Gaussian integers. So that's a concrete example of what you're talking about.
Yeah.
And if I pick another extension field other than...
Okay.
Yeah, go ahead.
Like every prime that is in congruence class 1 modulo 4 will split in Gaussian integers, and the ones that are free modulo 4 will not.
Okay.
And this comes from the Artin reciprocity law.
Okay.
Łukasz, these are all d ratio. Hold on. Wait. Łukasz, where are the functions you computed yourself then? Show off the thing that you actually made. Where are your actual Art and L functions? There it is.
Okay.
Oh, it's just not evaluated. Let's take an example.
Evaluated and no. Okay. So you take field extension, like splitting field of this polynomial, which are Gaussian integers.
Everyone on board so far. Step 1.
You get it Galois group.
Mm-hmm.
Now you take some representation of this group.
Okay. Yep.
Yep.
Yeah, I see it. There's a matrix representation of that group. Yep.
And now you take representations of something called Frobenius element for any given prime P.
You have to explain the intuition behind that, which you have, by the way.
Yes.
Frobenius is not really the best way to describe it, as you know.
Yes, Frobenius is pretty shitty to describe it. Okay.
Yes.
So you take your prime and you define its, and let's say it will split the prime that you chose. So you take 5 in Gaussian integers and it splits into 2 plus I and 2 minus I. Now you take whatever your new prime that lies above your original prime, which means now you take 2 plus I, let's say. And you look at the subgroup of the Galois group that fixes this prime that is chosen, and that's it. Like it may permute the other primes and do all sorts of stuff. It's a subgroup of a Galois group, but you fix one prime of your choice. And you call the group that you get decomposition group. These decompositions group are cyclic. So you get so they have one generator, and you call this generator Frobenius element or Frobenius endomorphism.
Here's what I think we need to do. Here's what I'm learning. In private, Łukasz is very good at explaining this, but it does take a lot of time. I think what we're going to have to do is Łukasz and I probably have to give some sort of joint presentation with slides, with particular examples, not just a notebook with a kind of a cascade of information. And there is, I've concluded from the work we've done so far, there is a straightforward, nice way to explain Artin reciprocity and how Langlands generalizes it towards non-abelian class field theory. It involves jumping over some puddles, which end up being oceans. And if you stick your foot in it, you get eaten by a shark, basically.
By the way, that for loop is a trivial nest.
That what?
The for loop is a trivial nest. It's just a nest function.
No, I hadn't seen that before. Yeah, that used symbols thing.
Anyway, that could be much nicer as a nest, I think. That's I'm missing something.
Okay.
No, but I can see that you're making progress here. It's just unclear to me. It's I mean, just in terms of the roadmap. I mean,
well, I'll tell you what the roadmap. There's no way you're going to know what the roadmap is. The roadmap is as follows. So we have, and it hasn't been conveyed here. We should just do another version of this where Łukasz and I present something jointly, and when we curate it more. I kind of had confidence that Łukasz would kind of just explain it the way he's explained it to me before, but it hasn't quite gone that way, unfortunately. What we should do is we'll have some other presentation. We'll explain everything that's happened with class field theory. Then there's a bridge from the number theoretic side of this to the automorphic analytic side of this. And we understand this bridge. We've begun to actually kind of probe this bridge, but it's not actually in this presentation. So the first thing is we should just explain the number theoretic arithmetic side of this to you all. And then we're going to do the same thing where we dive in and we understand everything on the analytic side, the automorphic side. Once we understand those two things quite well, there's yet another final step, which is you can understand all this in terms of groups and mappings and morphisms and this kind of thing. Once it's at that level, then there's going to be a very nice graphical, computational, perhaps multi-computational way in which we can actually show this, and then gathering up everything that we've studied and actually creating the meta-mathematical kind of web of all these connections will be the next step after that. But before we can explain what we know, we have to know it. And before we can even entertain the study of the Langlands group and the dual group, et cetera, we have to understand both the automorphic and the class field theoretic side. And actually, we do understand this first side. I mean, it's taken a lot of work, but we do understand it. It hasn't been properly conveyed. And I will say one other thing, which is it's not easy to convey. And I don't know anyone on the planet who's been able to properly convey it. What I will do, what Łukasz and I will do together, is I'd like us to be able to deliver perhaps the world's first intuitive, relatively understandable description of what all this stuff is, because it hasn't been done. And I think it can be done. It'll elide some details, but as an initial presentation, it can be done. The stuff is not actually that scary. And it's actually pretty easy to understand. It is conveyed properly.
I believe you. And I believe that I would strongly suggest showing explicit examples, tables of integers, extension fields, what things happen and so on.
Yes.
How do you package up, given a list of integers, how does it package up into an L function, et cetera, et cetera, et cetera. But I mean, more generally, the objective here is to understand more about metamathematical space. So far, this is all just mathematics. And
yes.
I guess my question is, what you're saying is, this is an environment where if you can understand mathematically the two sides of this analytic versus, algebraic kind
Number
of thing,
theoretic, yeah.
number theoretic thing, then if you have a good symbolic representation of both sides of those things, then the correspondence between them, then you can imagine from that symbolic representation, you've got all these different pieces on the two sides, and now you're going to see some correspondence from one to the other, which presumably is what, in the standard mathematical way of doing things, there's a mapping from one to the other.
Yes.
And I'm confused.
It's a functor in this case. Yeah. I mean, look,
Like
when we've done empirical studies in the past, right? We have leveraged considerable work that people have already done in formalizing everything.
Yes.
In this case, what we're doing is at such an advanced level, but it really seems like the most natural thing to study, that it's not like I can just ask Kevin Buzzard for everything in some library. They don't have it, right? And,
Okay.
I think in part people don't have it because this is not easy to understand. It hasn't attracted enough people, and there's no kind of general conversational way. Plus, there's no computational way to just speak about it concretely. And alas, this current notebook that Łukasz has is not terribly actually different in that regard.
Okay,
but we should do another presentation.
But the end result here, I mean, the things that we've studied in metamathematics have to do with networks of theorems and entailment cones between those theorems and things like that. What you've got here, as I understand it, is ultimately going for something where there is a mathematical, not a metamathematical correspondence, but a mathematical correspondence. But you're talking about functors, which is more meta than I would have expected this to be. I mean, I would expect by the time this is reduced to symbolic representations, that it becomes a straight mathematical mapping. But am I wrong about that? It's not a mapping of theorems. It's a mapping of this
object,
group, this whatever maps to this thing. It's not a meta mapping of this theorem, about something in geometry maps to this theorem in something in algebra, right?
Like the moment you have like this done mathematically on both sides, and you can translate one abstract expression, actually one symbolic wrapper to the other, then nothing really stops you from just taking this to the axiomatic side. You just take the equality and treat it as your theorem, and then you rewrite one theorem using the other. But for that to happen, we need to have this mathematic symbolic representation of this.
I see. So then the idea is, once you've got those correspondences, those mappings, you take a mapping and that becomes another level of object, and then you want to look at the mappings between those mappings. Is that right?
In some sense, that is functoriality.
It's
not just a morphism. It's not just a morphism. It's that you lift the morphisms from one to another. Yeah.
Yes. Okay. All right. So I think I understand now. So what you
all the constellations that you see on one side, so long as they do pertain to these L functions, there's going to be some. There should be some, or at least we want to probe, right? Langlands is always celebrated as this corresponds between two areas of math. This is basically ultimately going to be an empirical study of how much in kind of greater mathematical landscape does it bridge together. I think that's a good way of phrasing it.
A very naive way to think about it would be, you've got this plot that shows, a bunch of correspondences. Let's say very naively that you can plot on the x-axis, you're plotting, I don't know what, some feature of some extension field. On the y-axis, you're plotting some, I don't know, class numbery thing or whatever the heck it is, right? So you're actually able to say, in this representation of things, we've got this actual plot of this correspondence between the things on the x-axis, things on the y-axis. And now you've got over somewhere else, you've got a similar plot with completely different things on its axes. And the claim of this functoriality, I suppose, is that there is a way to make a mapping between the things that, one plot, another plot.
It's really that the functions are the same.
Yeah.
Even though prima facie they seem different if you don't know enough about the underlying theory.
But okay, but so we could do the same thing with Turing machines. We could say we've got two different Turing machines, and they're both universal, let's say, and we're going to say this one, with these specific inputs computes these things. This one with these specific inputs computes these things. And then we can ask the question, what's the correspondence between the picture that we get from one Turing machine, picture we get from another Turing machine? I mean, I've done similar things with cellular automata, where you ask the question, what's the correspondence between outputs for these two things? Yeah, okay, so I was looking for, wait a minute, you were just showing a picture there. That seemed very promising. I don't know what that picture is exactly of, but that picture seems highly promising. It's like,
this is an example of an ideal. Like,
okay. What's on the
x-axis?
What's on the
someone
y-axis?
asked what an ideal is.
What's on the x-axis? What's on the y-axis?
This is complex embedding, and this is ideal actually in what -2.
Okay.
And this is ideal generated by 1 plus.
Okay.
This is ideal. Do you see my mouse? So yeah, this is ideal generated by this element. And all the elements of the ring are just z plus z with -2.
But Wolfram, you have to explain what you should explain what an ideal is. I mean,
I think we should probably move on. Yeah. But the basic point here is, in the example I gave of Turing machines, there is no overarching mathematical structure that gives you, there's functoriality, so to speak, between two Turing machines that are both universal. And there should be a mapping between what they do. And you're saying that in this case, there's a huge chunk of mathematics that talks about, that sort of buzzes around that correspondence.
You see, but this is what I think is interesting is on the marketing side, Langlands is sometimes presented as like a gut in mathematics, as like a grand unified theory. As we begin to probe this, it appears as though it is a correspondence between, particular analytic studies of it seems to be much more specific and much less general than it's often presented to be. That's why I'd like to say, I think the way to frame this study is we'd like to show empirically, once you take Langland's functoriality and reciprocity, etc., once we look at these conjectures computationally, how much of how wide is its span actually in what we call metamathematical space? It could be the case that it's not as wide as it's kind of marketed to be. It does not really unify that much. And the correspondence between these automorphic and these Arch and L functions is not as surprising as one might suspect. Now, I think the surprise there might be that it's not this kind of miraculous correspondence as it's often portrayed to be. There's infrastructure below both of them that brings them together. And what we still don't know yet is just how general that infrastructure is and what it affords. It might be the case that it's surprisingly more rich than we think it is, but we don't know yet because we haven't studied it yet.
Like what you sort of do in Langland's program is you take like one polynomial worth of information.
Yes.
Your field extension. You define different objects using that information, using very complicated definitions, where error may be justified because your splitting field was easier to study when you encoded this a given object. And people, during the course of history, just generated a lot of this stuff using complicated definitions. And now they're trying to prove that it's equivalent, all these different objects. And you can translate from one to the other and maybe how to do it.
Right.
I'm going to make an overall proposal, which is I think that the way that Nick structured his presentation was highly effective, and we had good discussions. In this case, I think that Łukasz's work has to be even more curated than Nick's is. Kind of just presume that, well, never mind. What we should, and I think also with Carlos's case, Carlos is somewhat under the weather, and he also has a rather complicated project that probably should be subject to better. I mean, what do we want to? I mean,
let's just see. Let's just have a little look at Carlos's, if Carlos feels up to it.
I'm happy to present James.
You don't mind if even if there's not much time for Q&A or anything.
I mean, my presentation is about 10
Let's
minutes.
just see roughly what Carlos is up to. I really would love to see it.
Okay.
Yeah, I can definitely present in 10 minutes. It's not a problem.
Okay.
So does Carlos want to jump in here?
Yes. While Carlos
I'm very enthusiastic to see what how this. Maybe I'll actually understand this language thing as a result of what Łukasz is doing. But
yes. Okay. While Carlos is getting set up, I'll say something brief. Oh, I think we lost a few people. I'll say something brief about Carlos's research. Actually, Carlos, if you're about to jump in, maybe we don't even have time for my introduction. Maybe you should just go ahead. I'd like to give an introduction, obviously, because it's fun to talk, but you probably should just begin your presentation.
All right. Can everyone see and hear me?
Yep.
Yes.
Okay, so let me hide you for a second. So the project, as you can see, was called Sub-Axiomatic Foundations of Mathematics, and the basic idea was to take one of the examples that Stephen had presented in his blog post, in particular the one on emulating Boolean algebra with SK-Combinators. And so in some sense, let me just very briefly expand here. So very quick reminder for everyone, we have these SK-Combinator expressions, which are these head and bracket expressions, and these two rewrite rules, very simple, S and K. And the basic observation that you can read from Stephen's blog post is that you can essentially emulate functions that take arguments that are encoded with some expression in this particular syntax. And so, for example, this is the AND operator. So to compute something like true and false equals false, you can simply put the appropriate expression as a head of a two-argument function, and where your truth values are k and sk, and then you can run. In this case, we have this nest graph tagged just to show all the intermediate steps. If I can expand it, and then you can see how you go from this longer expression. You apply the rules in different positions, and eventually you get to sk. So this is a highly non-trivial property of this particular formal system, that these two rewrite rules actually make every single well-posed expression into a confluent rewrite system. So this is somehow the outcome of the outcome of Stephen's search, or one of the searches he did, and we have this encoding of what I believe are the minimal expressions that do the job for these binary functions.
The two arity operators in particular.
Yeah, that's what I said. Binary functions.
Yeah.
So one of the questions that James posed was, what happens when you just emulate an arbitrary expression, and we look at the states that happen between the sort of understandable, well-posed expression that corresponds to putting arguments in and the final evaluation. And of course, we could try and run random expressions of Boolean algebra, But what I thought would be interesting was to actually look at the evaluations of the binary operators, because in a way, that's on the Boolean side, something that is primitive. It's just the values they take. So they're just matrices of a pair of values. But on the SK-Combinator side, that's no longer primitive. You have for example, in this case of AND, you have this at least 3 steps that you have to take to get to a value that is, again, primitive, or it's just a value, right? So, or an expression that is a value. So I developed these functions to basically visualize these things. And so you can see, for example, for AND, which is the example above, oops. Oh no, just run it. Okay. I've used this color code, white for true, black for false, as you can imagine. And then you get to see the multi-way systems that give you this particular evaluations. So we can do this for all the operators. In particular, there is NAND here, in case you're curious to see. I can expand this. The graphics load. Yes. So as you can see, AND is quite simple. NAND gets more complicated. One first observation that is kind of interesting at this point that I thought about was some of these graphs look very similar. Obviously, this small case, you can see by, just by eye that these things are isomorphic. And so I did this little function that just tests for isomorphy of the graphs, and it basically plots some line between the evaluations that are isomorphic. And so you can see this particular pattern of symmetry for AND, which, by the way, doesn't correspond with the expected axiom of symmetry for the AND operator, which you should expect to see between true, false, and false, true. So that's some mystery there. And then, for example, you also have the NAND one, which has no isomorphy at all. And I think there were some others. Let me see. Isopairs of XOR, if I remember correctly, that have some partial isomorphy, if this computes in a few seconds.
Isn't it just one pair for XOR?
Well, we're about to find out.
Maybe. It's doing the graph.
While this is loading, there's a kind of a greater contextual. Yeah, it's just one.
So yeah, it's just the one. So one of the questions, as I said, was what is happening in between, right? So we have a clear interpretation for the initial value, the initial expression, and we have a clear interpretation for the final expression. But what happens in the middle? So one of the natural questions to ask is: would the operators themselves, the encodings that we have for these binary operations, appear in the in-between states? And so we basically scanned for both these patterns, in principle, just the expressions themselves. But then I actually thought that it would be much better to scan for the expressions applied to the correct number of arguments. So that's a little bit more constrained. And so we first did it for the multi-way graphs, if I can expand it. The graphics are loading slowly. Yeah. So let me explain briefly what this graph is telling you. Let me just expand this a bit better. So what this is doing, if I place this we have a nice tooltip that tells us that there is an OR instance in the first expression, as it should be, because we are evaluating OR for true and true in this case. And so the system evolves, and that OR disappears, and then further down the line you have true appearing, which is just the expression that we had up here. True is the constant true function, the KKK thing. And it happens 12 times in this particular graph. I mean, that doesn't really say something too meaningful, because some of them are just left untouched in steps, and they hit again. But that's kind of.
I'll just say something quickly in case people are either unfamiliar with combinators or with multi-way version. So effectively, as Carlos said, we can nicely emulate either one particular operator, or we can even compose them, so long as it's always just with respect to arity 2. And so we get the expected input state, and we also confluently reach a fixed point, which is also the correct truth value. However, because with combinators, it's just S's and K's. So the operators are also the arguments. And when you rewrite them in a multi-way fashion, you can select any particular sub-expression or position that is amenable to rewriting. And so what we want to understand is it is a nice emulation at the beginning, and it does compute confluently to the right truth value. But in between, the suspicion is that by rewriting over these arbitrary positions, the actual Boolean operators are going to get kind of thrashed around. And we want to understand the degree to which our actual kind of emulation is respected and recoverable, is retained as we do this, and the extent to which it's lost. And we basically just find kind of unintelligible, or at least seemingly unintelligible combinator content that nonetheless still manages to reach the correct value. That's just kind of a general overview of what we're doing.
This is the similar problem to, although a nicer case of it, to either the understanding machine learning problem or the understanding, like these automated proofs that like my one of Boolean algebra and so on. But this is a much nicer case because this case is much more complete. You can see the whole multi-way graph, and so I mean, it's very interesting case.
Yeah.
Of what mathematics can you fish out of the sub-axiomatic soup?
Yes. That's basically the idea. And so I decided to focus specifically on the evaluations because evaluations are in some sense atomic on the Boolean side or on the operation evaluation side. And here we already spot a lot of interesting structures. So by the way, the more detailed analysis of this should happen at the full expression. So here we have this particular rendering is the function that finds the fixed points, and I believe it's the one that always evaluates on the leftmost hit, if I remember correctly. And so we did this nice rendering where we have, if my mouse works, yes, we have nice tooltip that tells us which expression is being hit. I think this is detecting without the argument brackets, so it's just the actual sub expressions happening. We have the same function for the brackets because I think that's the proper one to search for because it's the mathematically correct one. I find this quite curious. There's this particular instance of false that just happens in the end a little bit, which you can see here actually, and at the end of this multi-way system. So with these, we basically have access to all the detail of the multi-way of the rewrite system of SK-Combinators that, as we know theoretically, should be confluent to these values eventually. So we have all this functionality. We can apply it to arbitrary evaluations of SK-Combinators, expressions of SK-Combinators that are rewritten confluently, and so we can ask more specific questions and start to do sort of more quantitative experiments if we wanted to in the future in this direction. But before I run out of time, I do want...
Hold on. I want to make one point here, which is
okay,
that,
sure.
One thing that you're doing, which I looked at a bit in my stuff on combinators, is empirical computational complexity theory, because every path is a proof of the result, a computation of the result, whatever you want to call it.
Yeah.
And there is a shortest path, presumably. It is the fastest way to compute, given this underlying stuff.
Yes.
And I guess, I don't know. I suspect there's an interesting set of things you can figure out about, for example, okay, you've got things like average time complexity. You've got things like, that's a little bit different. I mean, there's some notion of computational complexity theory that isn't just taking the fastest path here.
Yeah. I think that'll be relevant in the final points I'm going to make. So
okay, go ahead.
Hold that thought for a second, and I'll go to the end. So after having worked for a few weeks on this, I realized that even though we were conceptually thinking, especially James was proposing that this is an exploration of the sub-axiomatic foundations of Boolean algebra, really what we have been doing is two-element set model theory in a way, because at the end of the day, these 16 encodings that we listed above are just all the possible two-argument functions that you can define on a two-element set, right? So in a way, calling this Boolean algebra was a little bit of a stretch because, as I said, it's just model theory on a two-element set. So that gave me the idea that, okay, so this SK-Combinator framework really works well for model theory. And so I just extended a little bit to do it in arbitrary sets instead of just two elements. And it turns out that it actually works well. So you can, I discussed with Nick, by the way. Nick helped me a lot with coding because I was still getting familiar with many of the basic functions, and he was extremely helpful during these weeks. And so we developed this way of, first of all, we identified inert expressions of combinators, which I think everyone agrees that this should be somehow your variables in some kind of general sense to encode other things. And so I was curious. I haven't worked too long on this because this was a realization more towards the end. But I was curious to understand whether the KSK encoding, the sort of true-false two-value encoding that we had, somehow generalizes to any inductive like labeling pattern, especially knowing the example of arithmetic that has this sort of successor function that can be encoded naturally as well. And it turns out that I think it does generalize. It just happens that it's not very efficient. And let me explain what I mean by that in a second. So we have a way to search for this particular function I have here, searches for all the operations at a particular cardinality of set, arity of operation, and depth of inert SK-Combinator expression. So as you can imagine, if I do 2, 2, 2, that means I'm searching for operations that are binary on a two-element set and go up to depth 2 of combinator expressions. Depth 2 means that you apply these patterns twice. So in particular, you hit SSK, which is the operation for AND, which is the one that we had as an example. So anyway, this function, now we have this. We found out that it's quite expensive to go deep into these expressions. It takes a long time, at least for like domestic computers. But I did search for this particular list of operations. So these are all the operations that are defined, I think, up to depth 3, yes, and up to arity 2. So these are unary and binary. In particular, there will be encodings of the identity function and the anti-symmetric function, things like that. So the first observation is, and this is just to make the point that these are somehow inefficient, is that we find 22. Now, so these are not unary, these are only binary as well. So there's 22. And we know that at most we have 16 distinct operations on a two-element set. So this naturally leads to some notion of encoding equivalence, which if you have two expressions and they evaluate to the same thing, naturally you can call this equivalent in some sense. And we have a function that tests for this as well, which is nice. And it basically, I still have to take out the redundancy in symmetry because it's not tracing out, but except for that, it basically tells you which expressions are equivalent to each other because they evaluate. They have the same evaluation tables. It's not that they evaluate the same thing, but they have the same evaluation tables. So basically the other, so this is the...
Are those things, hold on, are those things equivalent if you plop them anywhere into a combinator expression with any evaluation semantics? Those two things will always be equivalent?
No, that's a very good point. No, so they are equivalent in this very specific sense of expression as a head to be acted on a number of arguments on the left, right, on the right.
Yep.
Right. So just a very primitive notion of equivalence, but equivalence is really an important notion here in this particular project, I think, as I will make the point at the end. And just the other aspect of this is probing actual axioms. So I feel like with a few more weeks of learning syntax and programming and in this more higher level Mathematica, I will be able to have some general functionality that will be able to be input a pattern that is basically an axiom, and then it will scan for this axiom in terms of combinators. In this case, I've only done some examples because it's kind of easy to do, but the point is that the function will do essentially what this is doing, I think. Especially if we are in the regime where we're doing evaluation as our emulation framework, right? By that I mean if we are taking operations that evaluate to a set of variables that are inner expressions that are somehow a labeling of the elements of a set. So in this particular case, you can see that we have a test for commutativity. So if you give me any particular expression and you want to test on a particular cardinality, so acting on a set of a given size, this function will tell you whether that operation is commutative or not. I mean, it's a very simple check. There's nothing mysterious here, but just to illustrate that this framework allows systematically to encode model theory axioms and probe for them explicitly. So, final thoughts, and then I'd love to hear Stephen's feedback and ideas and everyone else's. So, a few observations is that operation encoding seems to be strongly dependent on the cardinality of the base set. For example, I didn't show above, but the identity function that was sort of a reality check that I was constantly checking at every step of the way had completely different encodings depending on cardinality, which was, in my opinion, quite interesting to observe. This might be, I mean, you might change. By the way, the encoding of the elements of the set was always K, so basically nest S, right? So nest S on some inert expression, and we always took K as the first inert expression, and so you have K, SK, SSK, SSSK, etc. Equivalent encodings appear early in searching for depths. Many encodings turn out to be equivalent, and yeah, it seems to be computationally expensive. Now, the general points that I wanted to make, and to see if we can sort of trace out or map out some future directions, is this general idea of emulation. I mean, always wanted to say emulation with quotation marks, because this is not a formal idea that is perfectly well defined. But intuitively, what is going on is basically what's summarized here. Maybe I can make it a bit bigger. It's basically what's going on is this, right? Like, we have an expression on some formal system, in our case, Boolean algebra, on the right-hand side here, and states of that rewrite system can be naturally mapped to states of another rewrite system. Now, if the two systems happen to be confluent, then there's no more caveats to add here, because then you know that you're going to find a way to essentially map within the rewrite systems between those.
Sure.
And the idea is how to make this precise, to what degree this is to what degree this is a universal phenomenon between confluent rewrite systems or not, to what degree this maybe you can quantify this being the case or not, and so on. So I thought that doing the Boolean algebra or model theory emulation with combinators was a very good example, especially for me to learn how to work with these systems, but also to have a clear illustration, because I suspect, and maybe I'm curious to know what you think, Stephen, I suspect that this phenomenon of confluence in these formal systems in a universal way is not that common, or at least there aren't like all kinds of systems just lurking around that are like this. So I thought that was quite an interesting property, and my intuition for the next step is to really try to develop this concept of emulation in this abstract sense, that you have two rewrite systems, and I mean, the ingredients are obvious. I mean, we have some kind of mapping between states, and then there needs to be some kind of transitivity relation defined between states, which is the obvious one, because it's just the actual transitivity of the graph in terms of the rewrite system. And then we want to try to think about, is this compositionally rich? Meaning, if you have, for example, if you have two states that correspond to, say, for example, the and of true and false and true, we know that is symmetric. So those two things are in the space of states of SK-Combinators, different states, but they clearly, we know theoretically they are going to evaluate to the same thing. So can we actually fish out that fact from a purely rewrite theoretic or graph theoretic perspective, right? So these are the kind of questions that I've been thinking about, and yeah, I'd love to hear from anyone here.
This seems very interesting. Look, several points. I mean, so basically, you're trying to fish human interesting mathematics out of the soup of what combinators can do.
Yeah.
And the one criterion for human interesting mathematics that you're making is confluence, which is an interesting criterion. It may or may not be the ultimately, but it's a perfectly good criterion to look for. So you're asking for what set of essentially operators and objects do you have confluence for some, which you have these two examples of, the raw combinators and the Boolean expression type thing.
Yeah.
And I guess that's a good question. I mean, under what circumstances do you have these confluently closed collections of objects and operators? Seems like a good question.
Yeah, exactly.
I mean, I think that the general framework here, what I looked at eons ago is, given axiom systems, enumerate the axiom systems, figure out which ones actually appear in human mathematics. I think you're looking, I mean, obviously, universal algebra, the various different examples of systems that are, well, I don't know whether actually, here's a question. I mean, what your objects here, like for Boolean algebra, you just have two inert objects, namely true and false.
Yeah.
We also know in combinators how to make natural numbers.
Sure, we do.
Yes.
And so a question would be, let's say you're trying to do universal algebra in combinators, where you need variables of various kinds. I bet that in combinators that, I don't think, because you never need the variables, the combinator can just be this giant, any universal algebra expression can be built up as a pure operator type expression, where its variables are all, I mean, that's the point of combinators, the variables are all kind of clumped at the end.
Yeah.
So I guess the question would be, what do you need to do? Can you build, given an axiom system for universal algebra, can you construct can you get a combinator thing which is in a sense a model of that axiom system, if I'm not mistaken, right? The combinator thing will always be a model of the axiom system. Right?
That's exactly where I've spent the last couple of weeks thinking in the background, because I mean, one of the crucial points that was made at the beginning, and it was apparent throughout, but perhaps should be reinstated, is the fact that we are doing this evaluation based modeling, right? We're relying on the fact that you have a set. You have a set of labels that are SK encodings, and then we rely on the confluent property of the SK-Combinator rewrite system to actually evaluate expressions uniquely, right? And so one of the open questions that I have is, can this work in a more symbolic sense, right? Because so we basically have the floor of all the inert SK-Combinator expressions, and if you were to somehow find a way to implement, as you say, an arbitrary universal algebra-like expression with variables, right, into a combinator expression, maybe you have to run it to be inert, but hopefully there's some kind of one-to-one correspondence in this sense. Then it might be possible to say, well, this and this is just some syntax in SK-Combinator expressions, and then you run it, and then it evaluates to something, and that's just a derivation within your universal algebra system. The one worry that I have for that is that so far, I mean, your idea of finding something like the fastest path or some kind of complexity weighted path or something like that will be interesting. The problem is that confluence really is kind of dumb, and you're kind of thrown by the flow of the river all the way to the end, and in a way you lose information if you really want to evaluate. If you want to be well defined in this sense, you kind of lose information in some sense. So I'm not really sure how to do that, but I feel like it's an interesting endeavor. And then the open question is also, if imagine that it's not possible, or if it's possible, but the question remains, is this a property between general rewrite systems that they can be emulated? So in this sense of a relational property between rewrite systems more generally, I think that's, in my opinion, that would be the long-term sort of scope of this.
Okay, but I mean, okay, so the first point is, can you make a compiler that goes from universal algebra to combinators? That's one piece of this. A compiler where you're doing that by some kind of searching. I mean, it's a traditional compiler is very much an engineering type of object. This is a compiler where you're searching for a thing that will successfully do that. I mean, it's kind of like when people try and make, let's say, quantum computers, they are basically searching for a random physical system that will allow them to emulate, to do computation. Is it an ion trap? Is it a this? Is it a that? Similarly, here you're searching for a collection of combinator stuff that will allow you to do a particular kind of computation.
Correct.
But I think, among the questions one would like to answer, I would think, is there a natural ordering of mathematical constructs of the kind that we humans have come up with? That is, if it is the case that, it takes you this size of combinator to get to Boolean algebra, this size of combinator to get to monoid theory or something, how robust is that sort of hierarchy of where, of how complicated the raw material is for one of these things? Because I mean, in the evolution of human mathematics, there are certain paths where one's had, where one has a clear advantage. If the thing is like Boolean algebra, everybody knows how Boolean algebra works. That's a one-step thing. But the question is there a more robust notion of sort of the constructional complexity of some kind of theory?
Yeah.
I mean, this is, and the question is it the case that, for example, different rewrite systems, if you pick different base combinators, would you get roughly the same answer or not?
Yeah, of course. Yeah.
I mean, and my guess would be that that there is some robustness to it. My guess is that, yes, there might be one particular combinator that already has packed into it everything you need for monoid theory or something. But that most of the time, for most, I mean, this is a kind of a, sort of a claim, would be that most of the time, things are kind of, you're building up from a low enough level that it's more important what you're building than what the base material is. That will be a claim. May not be true.
Yeah.
What do you mean?
What's that?
What do you mean?
I mean that if you say, I don't know, I have the intuitive sense that Fibonacci numbers are simpler than primes, okay? If you try and build up Fibonacci numbers from raw material of combinators, that you'll get to them more easily than you'll get to primes. And even if you change the base primitives for the combinators, that will still be true. And similarly, in what we're looking at for empirical metamathematics, we have the sense that, I don't know, I have to look at the results, but I mean, the Pythagorean theorem is more complicated than some other triangle inequality type thing or something. And that will be robustly true, independent of the axiomatic foundations that you might pick. So in some sense, it's and then there's the question, oh boy, I mean, when you go sort of multi-way with all of these things, what does that mean?
So, Stephen, what do you think? Because if I understand correctly your question, doesn't this list of operator encodings kind of already tell you that it's kind of random at the SK-Combinator level? Because, AND has a short one, last has a short one, but then suddenly equal has a very long one. And
I don't think it shows it's random at all. I think it shows that I mean, these probably Boolean algebra is too simple. I mean, okay, pick a different set of combinators, you'll get a different distribution of what how big things are according to the primitives. I mean, this is a kind of study. I've done a bunch of these kinds of studies of what level of, given a set of primitives, how complicated is a human relevant construct given those primitives. And I think it's still the case that most of the things I've studied are too simple. You're still dealing with the kind of low-level starter type noise. But I think it's the case. I mean, the speculation would be the bigger picture would be, we have an intuitive sense that certain kinds of mathematical constructs are more complicated than others.
Sure.
is there some sense in which you can make it's not algorithmic complexity, it's some other kind of thing.
Yeah.
Some other, representational complexity of mathematical concepts. And in a sense, let me think about this for a second. Because in the end, one of the things we like to understand, once you have things ground down to combinators, there's sort of a better chance to understand the geometry of the whole sort of world of mathematically interesting propositions, once they're all sort of at a uniform level. If we just have them written down in math, it doesn't tell us sort of where they are in mathematical space. But if you grind them down to the sub-axiomatic level, we have the beginnings of more of a sense of that.
Well,
you don't know how tall they are in metamathematical space, so to speak, right?
Yeah.
Well, that's the question I'm asking: is there some robustness to their height?
Yeah, but one of the things that actually motivated me in sort of taking this approach of general rewrite system emulation and so on is precisely that question, because my view is that, and perhaps I want to be corrected on my opinion here, but my intuition is that rewrite formal systems only really have properties that humans are generally bad at perceiving. Like if you give me the SK-Combinators, I don't know if this is a particularly relevant rewrite system. It's only when I learn that it's confluent that it's like, okay, so there's something, and we have a set of inert expressions that is non-trivial and blah, 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 and then things start to prop up. So in some way, my intuition is that all these formal rewrite systems are living in some computational space, abstract computational space, and it's going to be some sense of relational properties between them that is going to reveal something like mathematical structures that human like. I believe that something being a mathematical structure that human likes is going to be more a relational property of different rewrite systems, because if you think about how mathematics is done in practice, that's what we do, right? We take some kind of system that we imagine or we see or we observe or we communicate, and then we translate it into some language, make some drawings or something, and then translate it again, right? So this process of emulation is actually kind of fundamental to the mathematical practice of everyday mathematics and the history of mathematics. So my intuition is that the concept of emulation is, when well implemented, will be able to detect for mathematically relevant theories in that it will be able to say, well, this class of rewrite systems share the Booleanness or share the arithmeticness or share all these kinds of things, right?
Well, you're basically saying things that are mathematically interesting have lots of functorial relations to other things.
Yeah, but in a very specific sense. I'm meaning functorial in this, quote unquote, functorial in the sense that they can be emulated and they have this rewrite system properties. In a way, what I'm trying to say is that you could just study rewrite systems abstractly in this context and be able to make statements that are very general, and that, for example, pick out SK-Combinators as particularly obscure because they don't have atomic things that look like the ones that we have used. Or you can take Boolean algebra, the symbolic one, not the two values true and false one, but the symbolic one, and realize that, right, so this one encodes exactly these axioms, and therefore we believe it to be so, right? And then, but obviously, because not all systems can do this, right? For example, we found this laws of form or whatever it was called that could do Boolean algebra, symbolic Boolean algebra quite well, but it couldn't evaluate true and false operations, for example, right? So it's not just everything goes. It's actually, there's some richness and some taxonomy that I think will be interesting. In what I'm trying to say is that, to me, the realm is the realm of formal rewrite systems, and trying to come up with good definitions in this context that are operational, that are computational, that can be coded, like this sense of emulation, I think will be very interesting. But before I forget, Stephen, what do you make of the fact that these expressions are so different in length? Because to me, this just speaks to the particular choice of the labeling of the two elements K and SK.
Well, I think that's where you have to look. I mean, if there are different, you've got different inert, just go look. I mean, you've
Sure.
got different inert choices of true and false. Just go see how robust this is or not.
Cool. Sounds very interesting. Yes.
But I mean, I have no idea how robust it is. I mean, that's okay. So here's the thing. I was interested in at one point, and there's some note in the NKS book about it. What number is the most obscure number? Okay, but of the numbers between, everybody says guess a number from 0 to 20, 1 to 25. Most people will say 21 or something, or people will say 7 if it's from 0 to 10. Right? It's what's the most obscure number. Okay, what does this mean? Well, so what I had a note in the NKS book where I had these operators for combining binary operators, where you make a number, like in these sort of games where you say, how do you make the number 51 out of ones and square roots and multiplications and so on, right? So the question is, what numbers are the most difficult to make out of a given set of binary primitives, binary operators? Right? And so you can compute what's the smallest tree to get that number. So I don't think I've had a real conclusion from that, but I think that's a question. I mean, you're kind of asking the same type of thing. What are things that are sort of, what kinds of constructs, I mean, for these Boolean operators, is there a most awkward Boolean operator, Boolean function, that's most awkward with respect to, most underlying representations? Just like, is there a number that is, you might say, what's happening here is you get an ensemble of possible representations, and you're asking, what's the distribution of difficulty of a given construct within that ensemble of possible representations? It's not a thing people have ever asked, okay? It's the exact opposite. Like for Turing machines, okay, you can say, this function, people ask, what's the average case complexity of this function, of this algorithm or something, where you're looking at different inputs to the algorithm. But this is a complete flip around of that. This is saying, if you look at the space of all possible Turing machines, what is the distribution of a given function that you're trying to compute? What's the distribution of difficulties of that function across the space of possible Turing machines? And I think that I mean, a slightly related question would be, if you look at like sorting networks and you ask, what's the distribution of correct sorting networks for a given size of sorting network? And are there sizes of sorting network, for example, that are, where is there one, what is the distribution? Is there one winner for size 17, and then all the other ones are really crummy compared to that, or what? So, yeah, I mean, I think, I don't know. It is, I don't know if there are awkward constructs, awkward Boolean expressions that are robustly difficult to compute.
Yeah, that's a good question. Yes, I agree.
Right. I mean, and then, for example, if it turned out that, and or not are much easier to compute robustly than NAND and XOR and so on, that's pretty interesting, because in human language, we have and or not, but we don't tend to have these other ones. And that would be a nice, if one could explain that, that would be an interesting thing. I mean, I think that, but I also feel like, one of the things one would like to get is this kind of meta-mathematical space. Let's think. I mean, what is the big picture here? The big picture is there's this kind of soup of things going on with combinators, and we humans get our mathematics by sort of leveraging, we identify things we care about, and then we look at what properties those things we care about have in the soup. And what am I trying to say? I guess that.
Well, what's curious is that if we just take some particular set of Boolean operators, as we saw empirically, those Boolean operators are often lost. I mean, we see that it still converges confluently to the correct truth value, but we really can't make sense of these intermediate operations.
Yeah.
But that's somehow not surprising, right? Because we have to evaluate eventually.
Sure.
Yeah, but look, what's the analog in natural science? Okay, we've got space flapping around and doing all its rewrites or whatever else. There are certain things that we identify in the world, like electrons and photons and so on, that whose properties are comparatively simple. So the analog of that here is, what are the mathematical things that you can get out of this kind of branchially extended metamathematical soup? That what's the natural science that you can do here? And that natural science, presumably, is the mathematics you can extract from this underlying structure. Just like in the case of physics, we think there are certain. So in this case,
which Stephen, which I think can only be properly formally detected by this idea of emulation formally, right? That you have the mathematics on one side is just one example of rewrite system that we know very well intuitively, and then you find this formal mapping into this, and you have some kind of strict criterion of what it means for it to be emulated within this soup.
Yeah, well, that's what's nice, because in the case of physics, on the one side we've got quantum field theory representing things, and on the other side we've got a bunch of rewrite rules, and it's so then it's non-trivial, and that's what Nick is trying to do, is to make the correspondence between the things we know, which are described in terms of field theory or whatever else, and this low-level stuff. What you're saying here is it's rewrite rules all over the place. It's these low-level rewrite rules, but also the higher-level mathematics that we think we understand as humans is also represented as rewrite rules.
Correct.
So it's a question of how those correspond. And yes, I agree. That's the and I mean, what I would expect in the language of quantum field theory, for example, there's this notion of effective field theories. That is, you've got some underlying field theoretic structure, and then you have some effective structure that is easier to understand that sits on top of that underlying structure. And presumably that's what you're looking for here, is an effective rewrite system. That is, what the underlying rewrite system is running 1 billion combinator operations, but you have an effective rewrite operation that is, in terms of summarized inert objects, for example, that's only got 3 steps to go, and it gives you, but so let's look at it bigger picture. I mean, what you're looking for, okay, actually there's the way to think about this. I mean, you're looking to catalog the slices of reducibility in this otherwise irreducible system. You're basically searching for natural laws. You can say it in many different ways. You're searching for an effective field theory, you're searching for natural laws, you're trying to find computational reducibility in the system. You're trying to find a summary of what the system, you're trying to summary of certain aspects of the system that you think are interesting. You want to find a much faster summary than the actual underlying machinery of the system itself.
Correct.
And you can't expect to do that in general, but you can expect to do that for things that are quotes. You hope to do that for things that are quotes interesting to you. Now, in the case of physics, the things which are interesting to us are somewhat defined by the sensory apparatus that we've been given, et cetera, et cetera, et cetera. In mathematics, it's a little less obvious, and that's what some of this mathematics discussion was involved with. It's less obvious what the things you care about are, because our mathematical sensory apparatus is less routinely defined.
Exactly.
But you're giving a criterion. You're saying, for the mathematician, let's say confluence is an important property, and therefore that's that's something which is a defining and confluence obviously has a certain reducibility associated with it. So I mean, that seems like a reasonable place to go. I mean, it seems to me like you're just wrapping your arms around this creature. It's a very big creature, so
Very big indeed. Yes.
But this is really looking like it's going in an interesting direction. I think the you'll get all kinds of. Look, the challenge. I don't know. You're not a natural science kind of person, but the challenge in natural science is you do a bunch of experiments, and then what the hell does this mean, so to speak?
Mm-hmm. Yeah.
And that's where it gets really interesting. And there are clearly fields of natural science where many experiments have been done and no big theory has emerged.
Mm-hmm.
The question here is this going to be like physics, or is it going to be like medicine?
Exactly.
Where you do many experiments and every experiment has its own separate, a separate life, and there isn't so much of an overarching theory of how things work.
Exactly.
And my guess is that mathematics is going to be more like physics, as we've claimed in mathematics work, than it is like medicine. And
Mm-hmm.
the reason is that somehow what we define as mathematics are things that have been emerged from us as mathematical observers, and that we could have defined something completely non-reducible, hard to understand. And anyway, that would be a thought there. But anyway, this looks like it's off to a good start.
Yeah, thanks. Yeah, exciting. It's quite interesting.
Does anyone else have anything to say, by the way? I feel
yes,
Tom, David, Xerxes, etc. For any of these projects, I ended up canceling the meeting that I was supposed to have at 5 because it's already 5:30.
And we don't yet have a time travel mechanism.
Is there gonna be another chance that I can learn about Langland theory?
Yeah.
And Alice
So
theory?
I'm
I'm interested in, but I think I couldn't follow perfectly today's talk. So
it's not your fault. I think what we'll do is Łukasz and I will give a joint presentation.
okay.
I think maybe hopefully even by the end of the year, just take everything we have, make some proper slides, give some examples, and I think between the two of us we can properly explain it.
Okay. And also, is there any kind of reference we need to read before see the talk, like a basic things, at least Gauss theory or something?
If you're interested in it, there's a nice 3-pager that the American Mathematical Society actually did put out, and I could share that with you. It's a 3-pager, but it'll take you some time to unpack.
Well, good reason.
Yeah, it took us a month to go through it.
Yeah,
what's that?
that's right, exactly.
It took us a month to go through it.
Okay.
I see.
It's concise, but no, I don't want to say that there's nothing that you can do to prepare. If you are really interested in this, we're happy to just, you can join the Langlands Club, the ELF Club, so to speak. But this should be a good presentation, the one that we give next, hopefully by the end, before 2023.
Yeah.
So it's most about like abstract algebra things. Is it some kind of that?
Algebraic number theory, field theory, group theory, analytic number theory. So far, what we have is mostly focused on representation theory.
That's why it's supposed to be a grand unified theory of mathematics, is it involves all these different areas of mathematics, which is why it's also kind of hard to understand, because the hope would be, I suppose, that you just understand it, and then you can flow from that to all these different areas of mathematics.
Yeah, but it's not clear that the purchase is that extensive. This is what we want to try and discern. It could just be that it happens to be something that thrusts through many of these, but that its actual extent is quite narrow. Or it could be the case that it actually offers this nice nexus between these different areas of mathematics. I think the marketing says it's the latter, and Łukasz and I, at least I do, Łukasz, you can speak for yourself, suspect that it's more narrow, but it happens to kind of cut across many of these different fields, even though what it says in its own right is unexpected, perhaps, but it's still quite delimited in its scope.
Yeah, it's sort of like one particular sculpture of mathematical concepts than
Right.
like the whole museum.
I see.
But the sculpture is tall enough that you can look at it from the different floors, so to speak. Even though it's just one thing. Yeah.
Yeah, if anybody wants to talk about Langlands, so I'm actually willing to have a meeting with you, like private, or we can stream this, whatever, and we can talk.
Sounds good. Well, I'm about to dive in myself to starting to work on observer theory, and I'm going to have many more. I mean, there are two projects that I'm really keen to get started on. Many of you may know I've been totally submerged in this crazy second law of thermodynamics project, which I've thought about this for 50 years. I thought it would be easy to write down what I figured out, but it turns out it's not so easy. But I'm very close to the end now. And I also made the arguable mistake of saying I better figure out what people have figured out before about this. And it's very interesting for you. I'm going to take 1 minute, 30 seconds to say something about this, because it's a cautionary tale. It's a meta-scientific cautionary tale. Because the second law of thermodynamics was developed in the 1850s and 1860s. And there were multiple formulations by Clausius, by Boltzmann, by Gibbs, and so on. And it was still a mess by 1905, 1902, 1903, that period of time. It was still a mess. And the problem was people then they started running after quantum theory and all kinds of other things, and people lost interest in it. But it was still a mess. And nothing's happened in 100 years. And those different formalisms for it, nobody knows whether they're equivalent.
I think people know that they're not equivalent. I mean, Daniel Sheehan has a textbook that talks about 23 different formulations of the second law, and he explicitly talks about how some are equivalent and not equivalent.
Right. But the core idea of the second law is much stronger than any of those formulations. The core idea is the mismatch between computationally irreducible underlying behavior and the computationally reducible capabilities of observers. That's the core idea. And that core idea is more general than thermodynamics, has nothing to do with heat and temperature and those kinds of things. That's the underlying strong phenomenon that leads to all these things. And then you've got lots of detailed sort of, can you analyze it this way or that way? That's the core phenomenon. And that phenomenon, it's more general, but it's also has places where it's not, where you can see there are limitations to the second law. Anyway, this is a whole different story. But the thing that is interesting to me is, which I've just been analyzing really, is how do people believe that it's all a solved problem? Right? It obviously isn't. They're obviously foundational issues. And why don't people know that? And why doesn't the average? And the answer is, basically because there's layers and layers of textbooks, and it doesn't really matter for the practical applications of thermodynamics. And it got lost somewhere 100 years ago. And basically what happened is people were interested in other things for long enough that the people who knew that the foundations were funky were gone. And so then it just builds from there. And it's kind of, and I haven't read, I will tell you that I've read the primary literature up until basically the work of Gibbs and then Ehrenfest. Ehrenfest was a student of Boltzmann's. I've read all that stuff now. I've not read the more recent stuff because my sampling of the more recent stuff indicated that it is basically a pure rehash of the stuff that was done, at that period of time. I mean,
there's Crookes fluctuation theorem. They've experimentally measured that you can have entropy decreases over very short timescales, and the characterization of those fluctuations has received. Right. Yeah. But there have been mathematical advances, in the 1990s related to this.
In the area of understanding fluctuations and so on.
Yeah, we can calculate the probability of an entropy decrease that wasn't doable 100 years ago. Crookes fluctuation theorem.
Well, you know what? Boltzmann has some nice papers, which I don't think have ever been translated out of German, that are about
Fair enough.
it's called the H curve. He called it the H curve, and it's basically a curve of, for his H function, which is his version of entropy computation. Has a whole discussion. In fact, he has a lovely thing that Klein commissioned Boltzmann to write a paper for mathematicians about the H curve, in which he essentially describes fractals, and describes the fact that the H curve makes a fractal. And I'm sure that I know there are a bunch of technologies for dealing with fluctuations. There are also technologies for dealing with things that are out of equilibrium, systematic ways of thinking about minimum entropy production. There's both minimum entropy production and maximum entropy production. So there's no doubt there's other literature. And I have to say,
So how would you state the second law again? Could you re-summarize how you think of it?
Yeah, I think the second law is basically the mismatch between the computational irreducibility of underlying dynamics and the computational limitations of the observer. And that's what, when you talk about what's a valid coarse graining, the answer, people have not been able to answer that. They just say, from Gibbs and Ehrenfest on, it's just like, oh, well, we have this thing which doesn't look in detail. I've got it in my historical piece. I've got all the actual quotes of what Gibbs said and what Ehrenfest said and so on. And it's, it's very vague. And I think that the characterization is that what you're doing is you're asking how computationally sophisticated is the observer, both the preparer of initial states and the observer of behavior. And what you're seeing is a mismatch between the sort of computational boundedness of the preparer of states and the observer of states, and the computational irreducibility of the underlying dynamics. And, so what I tried to do is start off from hard sphere gases, which are nice and, which is what everybody has studied from Maxwell on, that everybody was studying hard sphere gases. Boltzmann, all of these people, they all have, in fact, all those guys back in the 1800s, they knew calculus really well back in those days. And they have these very elaborate calculus things about spheres hitting and all the different angles that they were, and they didn't have computers, obviously. So they had, although several of them computed, actually, here's a good one that I just found. Kelvin did a Monte Carlo calculation of a bunch of things about hard sphere gases, which is something people, that's kind of a pre-Monte Carlo calculation, in which he did it by shuffling decks of cards and things. But anyway, so you start off with that and you see how, the essence of that dynamics are captured in much simpler systems where you're much more accessible computationally. So I think that's the thing, and there are all kinds of funky things that come out of this. But
does anyone have a question? Does anyone have a question for the fellows? By the way,
yes, that wasn't what I was trying to say before David.
Wait, no. You don't get another 10 minutes. Does anyone else have a question for the fellows before Stephen gives another long spiel? Presumably we're going to have some sort of actual live stream to talk about all the research that you've done, because I imagine there's a lot to say, and now is we're not going to get to all of it.
I just wrote I think I've written about 350 pages in the last little while. So yes, there's a lot. But the point I was going to make, which this was a sub-sentence, this was a sub-clause of the sentence. Okay, the actual thing I was going to say was that the next two projects that I really want to work on and see us work on are the observer theory and what we have been calling infracalculus, although it's a terrible name and we need to come up with a better name. But that is the systematic buildup from underlying hypergraphs, causal graphs, etc., to all of the kinds of constructs that we need to set up traditional mathematical physics.
It's just Stephen, it's just the physics project, this thing you call infracalculus. It's the physics project plus the generalization of it to multi-computation, which can be used for metamathematics and other studies.
Its relationship to the physics project is somewhat similar to the relationship of calculus to this
I know,
shows to mechanics.
but listen, from a public engagement standpoint, it's like no one's been working on the physics project. We're trying to renew the physics project,
Well,
putting it under,
people have been working on
putting
it on this group, but yeah, it's
not in a proper computation. What you're describing is basically the computational renaissance of the physics project, which Nick is already doing, and I think that packaging it under a more obscure name is a bad idea. You just say we're doing the physics project.
Whatever. I mean, that's a.
Yeah.
But the main point is, what I would like to see is, if I were looking at a calculus textbook, differential geometry textbook, any of these kinds of things, it tries to build up from a bunch of definitions like Euclid did and so on. From a bunch of underlying definitions, you build up a bunch of more complicated constructs. And that's what, I'd like to see that in a systematic way for the kinds of things that we're dealing with, hypergraph rewrites, causal graphs, all these kinds of things. And I think what Nick is doing is a contribution to that. I just, that's the thing I'd like to see. I mean, the other thing that is my little separate obsession, which I'm not sure how this group will relate to this, and we need to figure out how to do this, is actual physics. I've been thinking about, what I want to find Brownian motion for the physics project. I'd like to tell you another little historical anecdote, okay? In the 1800s, some people thought there were atoms. People built the molecular theory, the kinetic theory of gases, without knowing that molecules existed. And Boltzmann thought that when he put in discrete quantities, that it was merely an approximation. He did not think there were actually atoms, okay? And, in a sense, the last holdout, but by the way, there's a whole literature of caloric theory of heat, where heat was a fluid. There's all these things where people thought they were continuous. In fact, Einstein's paper on quantum theory, basically in 1905, on the photoelectric effect, very nice. Basically starts off by saying, we thought, we know that there are molecules, that material substances are made of molecules, but yet the electromagnetic field is still described as something continuous. Let us consider the possibility that the electromagnetic field is also made of discrete things. It turns out the one holdout in 2022, at least in 2020, the one holdout was space. It's the only continuous thing left. And so in some sense, if we were in the Victorian period, we'd be calling what we're doing the dynamical theory of space, because that's what it is. It's a theory of space, just like caloric was the theory of heat, in which heat was a fluid, and then it became the mechanical theory of heat, the dynamic theory of heat. That's what we're doing for space. And anyway, what happened in the case of the atomic theory, the real killer was Brownian motion, okay? But Brownian motion was discovered in the 1820s. So why didn't anybody know that, when Dalton was talking about chemistry and all this kind of thing, why did nobody put two and two together and say, there's Brownian motion, we can see it through a microscope, and by golly, that's evidence of the atomic theory of matter, okay? And that was basically Einstein and Smoluchowski. I haven't seen all the, it's a good Polish name, and I don't know all the syllables of it. And I've just seen it and I haven't said it. So I need to know how to, what is it? How is it pronounced?
Smoluchowski.
Smoluchowski, okay. All right, good. Anyway, what I want to find is the Brownian motion of the dynamical theory of space. In other words, I bet there's an effect that we already know that, if interpreted correctly, shows us that space is discrete. That's my latest little obsession, and I'm about to start studying rotation curves of galaxies and things like this, because I'm suspicious that dark matter is the caloric theory of matter. I'm suspicious that, because people had a theory of heat, that it was a fluid, and it was a pretty good theory. And Carnot invented thermodynamics on the basis of a caloric theory of heat, and even got it right, except that the underlying, ontology of what was going on was just completely wrong. And in fact, it was something that was more abstract. It was motion of molecules as opposed to a material substance. And there's a certain sense in which dark matter just feels awfully like caloric theory.
Well, I guess the point is, if you have a discrete and constructivist theory of physics, it's also background independent. So if you're actually constructing your space-time background, then the idea is, especially if it's discrete and if it's emergent, so long as there's some sort of heterogeneity that is perceptible given the instruments that we have, then you might be able to get actually some experimental evidence of that. I still think the trouble is we don't really understand how our constructors behave at scale, and that our expectations still aren't quite informed regarding what to look for. And I know you'll make the argument that people didn't really know what they were looking for when they did some of these other experiments. But
I'd like to point out that Brownian motion took 80 years from the time it was noted, that the phenomenon was noticed to the time it was interpreted. So yes, there's an issue with this. I mean, you have to have the right intuition to be able to identify, could it be the case? For example, you can go in two directions. One is and what you need is an intuition about what kind of a thing might show up from the discreteness of space. Once you have that intuition, then you can go and say, oh, by the way, do there happen to be any experiments that are in this direction? Right? Because that's what happened with Brownian motion. That's what happened. Well, that's what actually happened with quantum theory as well. Because Planck, you see, now I know all this history now. So this
wait. I don't mean to be obstinate, but the whole point of this stream is to give fellows feedback. It's not a preview of the talk that Stephen's going to give. I know people are interested, but we've convened it for this purpose. There are people on this call who haven't even spoken. Maybe they have questions. Let's just give them the chance to ask.
Fair enough. Fine. Yes.
Okay. Like
so who has a question?
Or David or someone. I mean, is there you've sat through 3 talks. Is there anything that you'd like to, that you have to offer? If you don't, then it's okay. We can go back to learning about thermodynamics. But
I was just going to mention with Langlands, I feel like I somewhat agree with the assessment that it's clear that there's primarily a bridge between two things that makes contact with a lot of interesting mathematical ideas, but it doesn't mean it's unifying all of mathematics. I don't know, to me, Topos theory might be more of something in that direction, but both Topos theory and Langlands are kind of outside of my wheelhouse, but just my 2 cents.
My impression is that Langlands is much more, connected to the mathematics as opposed to the more meta-mathematics side of things. I mean, it seems to me that, yeah.
Okay.
I'm not sure what it means to say unifying mathematics. Because this even in physics, the term unification has many connotations, and I think a lot of physicists now will agree that maybe it's more a kind of fantasy to think of unification as if there is one reductive thing from which everything comes out. And the kind of main reason I say that is because from recent kind of inputs in homotopy type theory, people are beginning to realize that there are many universes of mathematics. So in that sense, I don't know whether Langlands should be seen as a unification program, or it should rather be seen as one of these bridges between these universes that Topos theory and homotopy type theory are already giving us ingredients to at least describe to some extent. So in a sense, if Langlands does want to say about connections between different areas of mathematics, some of the constructions that they are coming up have to touch upon, or at least have to, in some sense, be explainable from the way people are trying to build constructive mathematics and universes of mathematics in modern day foundations of homotopy type theory. At least from the existing literature, people haven't really described the Langlands program in this context. I'm not sure why. I don't have enough knowledge of the Langlands program to comment on whether secretly they are not really taking it seriously enough for this purpose. because of the reasons you all just stated, that it might be way narrower than is advertised? Who knows?
No, like it's not at all that it just can take arbitrary mathematic theory and translate it to the other. Like, what we're learning is that it's more like actually 5% of each mathematic theory, but like almost every of them, and you just combine it with
I see.
this framework. Like, it uses some modular forms, and then there is correspondence between some modular forms and some L functions.
I see.
And
But we don't want to judge prematurely. We should really understand the full
Yes.
correspondence. And also, there are really two flavors of Langlands. There's arithmetic, and then there's also geometric Langlands. And I think understanding both of those is going to be. We should really do that before we begin to disparage it too much.
I see. Just a small,
On the universe question, though, to speak of an even more ambitious potential future goal, I do wonder if interuniversal Takemiller theory, which is very, very poorly understood and seems like it makes even Langlands look quite narrow, considering its kind of generality that it has. Perhaps studying these things called these Hodge theaters and these like very larger universes of mathematics, which is also still in number theory but much more general. If that will be more satisfying in terms of the generality, but we're not even close to doing that. And if we want to learn it, one of us has to learn Japanese and go to Kyoto, because that's the only way that you can really study it.
In this context, I think since you mentioned this, Peter Scholz has recently been looking at some of these verification processes for the interuniversal Teichmüller theory, and there were some objections he raised. They are not conclusive, but there were some issues he pointed out in this context.
Yes, they object to corollary 3.12 specifically. So there's a whole debate about alien ring structures and corollary 3.12. Literally, Kyoto, they teach mathematics in Japanese. This is what I saw on the website. So if you want to actually go and study with Mochizuki, you actually have to learn Japanese. So it's yet another obstacle to actually understanding this Takemiller theory, unfortunately.
But I mean, just to say, it seems like the thing that you guys are doing is to concretize what is going on in the Langlands sort of world. And, I've never seen that. Maybe it exists, but I've never seen kind of the experimental mathematics. Forget meta mathematics. The experimental mathematics of Langlands. And once you can get the experimental mathematics, you have a chance of being able, maybe the thing will automatically sort of, power itself up to the mathematics. I think it's quite likely, actually. But that's
everything. If you have everything expressed symbolically, that, as I said, you can basically take the equality of two expressions and turn that into an axiom or just your logical statement and work from there.
Rule. Yeah, a rule that's operating at a very high level.
Yeah.
And as I said before, there is a group theoretic way of expressing all this, but we're not there yet. That'll probably be review number 3. First was this one. We'll have some follow-up lecture at the special, and then we'll have the one on the automorphic side, and then we'll actually do the real group theory in Langlands.
Maybe one more comment about examples. I don't want to just leave it like that. We learned during this that finding examples to various stuff in Langlands is very hard and not so much enlightening. There are a lot of distinct cases that are solved, but it doesn't generalize. It's like asking, give me an example of how to solve this Diophantine equation. And I can provide a very complicated method of solving this particular equation and maybe 2 others if we're unlucky, and then it'll be it. And it won't tell anything more, it won't give you any intuition. And actually the very statement of the main theorem of this class field theory, Artin reciprocity, operates on some abstract concept of these Frobenius elements. And if you want example, they live in this abstract space as the representations of the decomposition group and something. If you want a specific example, then this, I can give you like Dirichlet character. This is specific example of this, but the statement that it is an example and what actually are the examples is like the Artin reciprocity tells about it. You have this thing defined abstractly, and what you're trying to model is the statement that it has examples.
Yes, I mean, one thing that we've found that's somewhat disappointing is I presumed originally part of the elegance, and we might still be wrong. I'm still going to reserve some judgment, but I presumed in the beginning that part of the elegance was that there was this kind of machinery that was afforded by functoriality that was going to make it easier to do actual mundane calculations in class field theory. It turns out it's what Łukasz is suggesting is it's really the opposite. It's that when you compute examples via some other means, it happens to fall cleanly into this general kind of correspondence and general relationship that they posit without any particular examples.
To make one comment, which is, I'm totally unskilled in this area, but here's an observation about equations and things, which, standard observation from the building of Wolfram language. When it comes to polynomial equations, inequalities, and so on, over the reals and the complexes, we have one master algorithm which just, crushes them all. I mean, it's our sort of version of the Tarski type algorithm. Okay. When it comes to Diophantine things, we have 30 algorithms, last I knew, that all pick away at different parts of the Diophantine universe. And, that's in a sense a consequence of the fact that, over the reals and complexes, it's decidable and you can crush it, even though it may be kind of technically difficult. But over the, over the integers, it's not decidable. And the on-the-ground consequence is 30 different algorithms that pick away at different cases. And what you may be seeing is that, there are many cases. I mean, I don't know whether it could be the case that only the things that are, the particulars that are, that are the, resolvable Diophantines are even on the table to discuss. And that the vast ocean of Diophantine equations that are not, that have undecidability, are universal, and so on. I mean, what will the Langlands machine? So this is what happens with the personalization of things, because I remember Bob Langlands from when I was at the institute, and it's a but anyway, the other Institute for Advanced Study, it's a what am I trying to say? The Langlands machine, so to speak, what's it going to do if you feed it one of these undecidable Diophantine equations? The answer is it's going to say, I don't have anything to say about this. It's going to say, I only deal with the cherry-picked ones. Is that a fair?
Like the theorem in Langland states existence. Like you have representations of your Frobeniuses, and the Artin reciprocity tells you that every representation that you find will be in the form of in terms of Q, let's say, Dirichlet character. And for every Dirichlet character will be some Galois group that representations of Frobeniuses thereof will give you this.
Okay, so it's an existing
character. But you only begin with some field extension that is the splitting field for some polynomial. So by the time you're actually working with whatever field, and you've taken the representation and the Frobenius endomorphism, et cetera, you've already decided there's some particular, polynomial that already has a splitting field. So you've already kind of done all that. You've made those presumptions in the very beginning, which is probably to Stephen's point.
Yeah. We should probably wrap up, unless you want me to start talking about the Brownian motion of dynamical theory of space, which is, I mean, I will say that I am very actively looking for, I mean, we really need to, the project that I tried to get done a couple of years ago about looking for d-dimensional generalizations of the general formulas of physics. I really need that project, and I'm going to end up doing that project because I really need to know, if you look at binary star systems, how do they detect dimension fluctuations, or do they? How does the structure of black holes vary which it does a lot between different dimensions? How does the in particular, well, as I say, the idea that, for example, you can parameterize, things like dark matter and dark energy are so deeply sort of historically resonant with the caloric theory of heat. I just can't avoid that analogy because it's just like everybody thinks there are particles. Particles are what we know, so let's put particles here, and it just feels like it's if all you knew was fluids, you'll never think of the microscopic motion of molecules, and that was a severe ontological error, so to speak. And my guess is that that a bunch of the anomalies, and I don't know if anybody knows I think I sent out some mail about this, the PPN formalism, parameterized post-Newtonian formalism. I bet David knows that. He's nodding his head.
Yeah. I've studied post-Newtonian and post-Minkowski expansions a little bit.
So my question is this: I want to know, in variable dimensional space, what on earth happens to PPN? In other words, does PPN parameterize? Is the parameterization of PPN applicable to variable dimensional space in any way? I'm sure nobody's ever thought about it. But the question is, what people have done is to show that, various PPN parameter regimes are inconsistent with observations. But that doesn't really help you if PPN does not cover variable dimensional space. That's my question. Right? In other words, saying I don't remember what the names of the parameters are, but saying it's general relativity and it's perfect. Well, clearly it's not perfect because we've got a bunch of phenomena we don't understand. And
One thing that would be helpful. Oh, no, go ahead, David. No, please.
I was just saying, largely, the candidate is either like particles, as you were saying, or modifying Newtonian dynamics itself. I don't know if you're suggesting there's some third option, or
yes, that's what I'm suggesting, which is to modify the structure of space, which is different from this modified Newtonian gravity type idea. I don't know how it's different, and that requires a bunch of actual physics to work it out. Okay, so for example, what does gravitational lensing look like when the lensing is not through curvature but through variable dimensional space? And my guess is that you get a fractal image, but I don't know. Okay, and that's an example of something that you could just look at. People have, their actual pictures of gravitational lensing, right? And some of them are very much not fractal. But for all anybody knows, there's other gravitational lensing which is more bizarre and which the image processing algorithms that have looked for gravitational lensing would not pick up. It's an example.
One thing that will be helpful, though, I've said this before, is we've seen examples, say, of hypergraphs, which is a model of choice, that after a small number of operations happen to have fractional dimensions. Now, presumably, our universe has just been run for a large number of operations. So I think it would be helpful, especially if you're going to try and make this amenable to empirical or experimental observation, is trying to actually formulate some expectation, which is if you're saying, I expect that the dimensions will be fractional or there'll be fluctuations. Of what magnitude and why, for instance, if you just take the devil's advocate position, why do you not suspect that there's overall a significant amount of stabilization once the universe has been running for a significant number of steps and it has a certain scale?
I'm sure there
is. So then the fluctuations are at best minute.
Well,
quite minute.
Yeah,
right.
Sure. Look, I'd like to remind you again, this is what I get from learning history. History is very useful, History, I really recommend learning history. throughout the 1800s, nobody knew how big atoms were. They had no idea how big atoms were, but they built kinetic theory of gases without having any idea how big atoms were. Literally, I mean, they knew that these relations between viscosity and pressure and all this kind of thing, they knew all of that stuff because, you know, the parameter, like the mean free path, depends on the size of atoms, but they didn't need to know that. There were a bunch of other relations that didn't care about that. So it is in our theory of physics that we don't actually need to know the size of the elementary length to make a bunch of deductions. But, you know, if you want to measure the fluctuations, which the thing which is completely not obvious was that something like Brownian motion will be observable. Right? It could be the case that atoms are just too small. That's what people like Boltzmann thought, that they would just be too small to see. There would be no effect that would see them. And, you know, Loschmidt, for example, had computations of the size of the atom based on things like mean free paths and so on. And that was, you know, that was another way in. It was a more direct way.
But I've said this before again, the comment is not about whether or not it's experimentally feasible or not, right? It's just that it seems as though on the theoretical side, it could be somewhat better posed, for instance.
Of course it
which
can.
is like,
yes.
But
But one wants to go in both directions, because the fact is, if one already has a lot of intuition about how the thing works, at least I feel I do, and, you know, given that intuition, then like for example, once you have the intuition that the electromagnetic field might be discrete, then, as old Einstein did back in 1905, you go looking for phenomena which might reveal that discreteness. And oh, you find the photoelectric effect. Oh, you found this thing that Planck had done, which Planck didn't think was important. That was, you know, this fact that if you use Boltzmann's formalism and you don't take the limit of packets of energy being of zero size, you get this other distribution that happens to
I guess the point is, though, let's say even if you happen to find an experimental suggestion of discreteness, you know, there are all kinds of different discrete theories of physics you could have, and so it doesn't necessarily confirm our theory unless our theory is more specific besides just, you know, it's discrete and the dimensions are fluctuating, right?
Look, the problem that people have had for the last, I don't know, nearly 100 years is that most approaches to discreteness in space end up with all kinds of crazy inconsistencies. And that, you know, so you can say, I mean, look, it's like people had in kinetic theory, in the, you know, people had ideas. Okay, so, you know, when Boyle in 1660 was first trying to work out the spring of the air, which is, you know, pressure in air, right? He had two theories. One theory was that Descartes' vortices were rubbing up against each other and bouncing off each other. His other theory was, as he put it, it's like a fleece of wool. It's basically a bunch of points, and they have little springs connecting them. Okay? You know, both these theories are, I mean, I don't know. I think most of the discrete space theories are pretty much at the fleece of wool level. And, you know, we happen to have one that isn't. But I just don't think that that's, the main point is, you know, well, it's like the kinetic theory of gases. It doesn't actually matter in detail whether they're hard sphere gases. People thought it did. People thought it mattered what shape the molecules were. There's a whole ridiculous literature on that. It doesn't matter. And so it will be with our stuff, that in the limit, it won't matter. Those details won't.
Well, but if you have to construct everything, like you have to construct particles, then your choice of constructor is going to matter. And the interpretive framework by which you study the relations of the things that you construct do matter, right? That's what I'm saying. I mean, I'm saying just observation of discreteness. Okay, you're saying maybe most of the other discrete theories are of questionable quality. But but just because there is discreteness, I would not say that the rest of our theory is trivial, especially if you have to construct everything. There'll be all kinds of rules that give universes other than ours, and there'll be all kinds of interpretive frameworks that, when applied to the constructors, also don't give the right thing.
And it's also unclear because it's all subject to interpretation. It's like how you differentiate between whether you have some fractional dimensional effect that is depending on it or the actual particles. It's like another purist would say, would just come in and say it's just another field that nobody considers, it's just those different dark matter particles instead of fluctuation of dimensions, right? It's like it's all subject to interpretation. It's just the matter of which one is more appealing than other.
No, it's a different thing. There's a more pragmatic issue. Which one gives you the right intuition to know what experiment to try to do? And that's something that really matters, which intuition you have. If you have the wrong intuition, you're just going to have the completely wrong conclusion about what to try to do.
Yeah, I mean, that's what I mean by appealing. More intuition is also more appealing.
Right. I mean, and this is, anyway, I think it's important to work from both ends. I think it's important both to work on the formalism and getting the formalism sort of more developed, because I agree, I'm frustrated that I can't, and this is what I'd love to see from what Nick is doing, to really be able to, in some very Euclid-like way, go from the underlying, what we have in the theory is events and, connections between events or something. And then from that, we derive this and this and this. This is the definition of a world line. This is the definition of whatever, to be able to very Euclid style build up everything.
It's being constructive.
Yes.
This is what we mean.
Right. But I think the place to start there is by trying to build up sort of known structures of mathematical physics from the raw material of this discrete structure that we have. And, you can do it from causal graphs, you can do it from the hypergraphs. Both, I think, are interesting and related, obviously. But, I mean, that's what I'm very much a believer in being able to write down the definition, what its consequences are, and make it computational. And, for each definition, it's like, and we can actually run all these examples with this definition. That's my theory of the case.
Part of why we began with energy, mass, velocity, these kind of values, though, is those seem to me to be really the most fundamental ontologies that you want to be able to identify consistently when you actually are constructing things, right? Fine. Because even if you have a particle or something, I mean, all of these objects have to have properties, and so you have to have those basically a priori. Because if you don't, then you won't be able to say whether or not your constructions actually satisfy them or not. So that's why it seems like this is the first step that we're taking.
I mean, I would start with the structure of space, but it's okay. I mean, starting with energy and so on is fine. I mean, I think what you're,
studying the structure of space is good too, but then, so it's like, okay, you have your space, it's being constructed. Then there actually have to be objects or desiderata of some theory that are in it.
Space on its own can tell you nothing, because it has to have, the space doesn't mean it. In fact, okay, history fact for you guys again, our friend Descartes, okay, had the following observation. He said, if you want there to be a non-zero distance between 2 points, there has to be stuff that is communicating from one point to another, which is basically what we say as well. So in other words, in traditional mathematical physics, you don't need that. 2 points are just sitting in different places in space.
On a manifold,
the way they are. Whereas Descartes said, you can't do that. If there isn't something that's sort of a chain between them, they will be together.
Yeah, and you have to construct that thing that mediates between them.
So 16, whatever it was, 30 or something, Descartes was saying that, but that got lost somewhere in the intervening years. And now we're back saying the same thing. We need to wrap up.
Yes, and Carlos is
I think David might have signed himself up to get a draft of my 300-page thermodynamics thing here. It's
sure, yeah.
Well, so one thing you can tell from all this is, so the Institute has launched. We have a number of these projects that are underway, And Stephen has been kind of otherwise preoccupied doing other kinds of research. Once Stephen is available, there are projects that Stephen wants to do too. And so Stephen will be working with fellows on particular projects that he wants to do. And we'll also have these other projects happening in parallel. So there'll be kind of an uptick in activity probably as Stephen gets involved. And he brings, Nick and other people involved in doing observer theory and this kind of computational construction of objects in mathematical physics, aka
observer theory is going to be great. And what Nick is doing is a good precursor to that. In fact, what Carlos is doing is also a good precursor to that. And it's and I have and actually, okay, my parting comment is this stuff in thermodynamics has been super useful in understanding how to formulate observer theory, because I've realized that it's a simpler case of observer theory than some of these other ones. Anyway, all right. Well, we should indeed wrap up. And nice to hear about all this stuff. We're hearing a lot of background noise and typing, so that's right.
Yeah.
Thank you for the talk.
Okay.
Thanks, everyone. And you'll get an invitation for a real Langlands talk, hopefully sometime for the end of the year. Yeah. Thanks, Stephen, for your comments and your feedback, and for everyone else for attending and for participating. This is the first of many of these. There's some lessons to be gained from this, and you'll all be invited to all the subsequent reviews as well. All right. Cheers, everyone. Thanks.
Bye.
Bye.
Thanks. Bye-bye.